Hello, my dear students. I hope you all are really doing great. First of all, I welcome you all on this amazing platform of PhysicsWallah English channel. Students, if I talk about today's lecture, that's lecture number 3 of the ongoing champion series for JEE mains and NEET aspirants. In this lecture, we are going to cover the most important chapter or the topic of organic chemistry, and that's reaction mechanism. Students, in this lecture, mainly we'll cover first the basic strength, then we'll talk about nucleophilicity, nucleophilic strength, then we will talk about living ability of the living groups, and then in the end we will talk about different types of reaction mechanisms like nucleophilic substitution reactions and elimination reactions. So students, this particular chapter is really important, and you may say it's the backbone of organic chemistry. You may also say it as the advanced application of GOC. Whatever we have learned in the first lecture, we are going to do the applications of that particular lecture. So without wasting any further time, let's start our discussion. Students, let's start our discussion on the first topic, and that is the basic strength of organic compounds. Students, if I talk about the bases in organic compounds, they are nothing but the electron-rich species having tendency to accept protons. Mainly in organic compounds, we define base as the electron-rich species having tendency to snatch protons, to accept protons and form a sigma covalent bond with protons, right? Now we are having 3 different types of bases. First one is Arrhenius base, second one Bronsted base, and third one is the Lewis base. If I talk about Arrhenius base, they are the species having tendency to release OH minus in the aqueous solution. We have studied it from class 9, 10th onwards. The second one, Bronsted base, they are nothing but the species having tendency to accept protons. In organic chemistry, mainly we are going to talk about this Bronsted base itself, right? They are having a tendency to accept protons. The third one, Lewis base, they are the electron-rich species having tendency to donate pair of electrons to H+, right? Arrhenius base, OH minus releasing tendency, Bronsted base, proton acceptance tendency, Lewis base, electron pair donation tendency to H+ mainly, or to any species. Okay, let's move ahead. Now, the second most important terminology which we are going to discuss is basicity. How do we define it? It's nothing but relative tendency. Here we are going to define the tendency. The tendency to accept H+ and form a sigma covalent bond is nothing but basicity of a compound. Let's write it. The relative tendency, this word relative is very important. Relative tendency to accept proton is nothing but H+ and form a sigma covalent bond with H+, right? Now let us try to understand this basicity with one example. I am having ammonia, NH3, and I am having water. Now I simply say you to compare the basicity of these two compounds. Okay, how will you compare? How do we define basicity? The relative tendency, how easily this ammonia or this water will accept proton or will form a sigma covalent bond with protons will decide the basicity of these two compounds. Now in case of ammonia, the lone pair is present on nitrogen. In case of water, the lone pair is present on oxygen. Okay, H+, H+. Which one will have higher tendency to donate its lone pair and form a sigma covalent bond with H+? Nitrogen. Why? Nitrogen, being less electronegative, will have higher donation ability, right? So it can easily form, or it can readily form sigma covalent bond with this H+ and form this NH4 plus. Right, student? If I talk about water, here the lone pair is present on oxygen. Being more electronegative will have relatively less donation ability. Okay, so here I will have O, H, H, H positive. Now, which one is easily formed? NH4 plus is easily formed or H3O plus is easily formed? NH4 plus is easily formed. So can I say basicity of ammonia is higher as compared to that of water? Let's try to understand it in a more better way. I'm having a species Y minus. Now I'm going to define basicity for this. This basicity is nothing but the tendency to accept protons. So this Y minus is going to accept one protons and will form a compound HY. Now, can I say this Y minus is a base and this HY is nothing but the conjugate acid? Right, student? Whenever we add one proton to a species, the conjugate acid is formed. So this one is the conjugate acid. From acid, if I am going to remove H plus, we are going to form conjugate base. We have studied it in first lecture itself. Now in a base or in an electron rich species, if I add one H plus, we are going to form conjugate acid. Now the basicity of this Y minus will simply depend on the stability of HY. Higher is the stability of HY, higher the stability of HY, better is the basicity of Y minus. Now students, you know stability is all about related to thermodynamics. So can I say this basicity is all about a thermodynamic concept, right? It has all about this. The basicity of this Y minus will simply depend the stability of this HY, right? Higher the bond energy of this HY, better is the basicity. How? See, higher is the electron density on this Y minus, it will have higher and higher tendency to form a sigma covalent bond with H plus. It's an electron deficient species. More is the electron cloud, it will have a higher tendency to form a sigma covalent bond with this H plus, and higher will be the stability of this HY. So can I say higher the electron density, better the donation ability, generally higher the basicity of a compound. I hope you understood it. Let us move ahead. Now students, in organic chemistry, most of the time you will see question, compare the Kb value, right? Compare the pKa value, compare the pKv value of these organic compounds. Whether in JEE Mains, JEE Advanced or NEET, everywhere you will find similar questions. Compare Kb value of these organic compounds. Okay, so how do we compare the basic strength of a certain compounds? The first is compare their Kv value. And how do we compare Kv value? Simply, it depends like this. I'm having a base RNH2. I'm taking it in an aqueous medium. If it is a base, can I say it will have a tendency to snatch H plus, and here this water will act as an acid and it will form a compound RNH3 plus OH minus, right? If this RNH2 is behaving like a base, then it will have a tendency to snatch H plus from water, form a compound RNH3, and it will release OH minus. Now, this process is going to be a reversible process. For this reversible process, I can define equilibrium constant Kb. This Kb is nothing but base dissociation constant, right? We have studied acid dissociation constant. Now we are going to define base dissociation constant. Higher the amount of OH minus released, higher will be the value of Kb, and higher is the OH minus released, can I say higher will be the basic strength? So can I say basic strength of a compound, basic strength of a compound is directly proportional to Kb. Higher the Kb, higher is the basic strength. One more thing, students, we have studied basic strength directly proportional to Kb, inversely proportional to pKb. But can you remember the Kb value of all the compounds when you are asked to compare the relative basic strength? No, it's very tough to remember the Kb value. So, if you are asked to compare the relative basic strength, we have a certain methods through which we can easily compare the relative basic strength. And how do we compare? Let's see. I'm having a base RNH2. This is the base. It's treated with an acid HA. What is the function of base? To snatch H plus. What this RNH2 will do? It will snatch H plus from this acid, right? And will form RNH H positive, right, student? Okay. How these two compounds are related? If this one is base, can I say this one is nothing but conjugate acid? Conjugate acid base pairs simply differs by a proton. If you add one H plus to a base, you are going to get conjugate acid. So this one is the conjugate acid. Now the basic strength of this particular compound will simply depend on stability of this conjugate acid. So students, now it's time to discuss what are the different criteria which affects the stability of this conjugate acid or which affects the basic strength of base. Let's start our discussion on that. Criteria for deciding basic strength. Student, if I talk about the basic strength of compound, mainly we discuss basic strength in two different medium or in two different solvents. One aqueous solvent, one gaseous solvent. Let's first of all talk about basic strength. Basic strength of a compound in gaseous solvent, gaseous phase or solvent. Okay. Student, just now we have studied RNH2 H plus forms RNH3 positive. We have studied the basic strength of this RNH2 will simply depend on the stability of this conjugate acid, right? Now, what are the factors which will affect the stability of this conjugate acid? Can I say, if this R is an electron donating group, can I say in that particular case, it will release electron towards nitrogen. The electron density on nitrogen will increase and the stability of conjugate acid will increase. And higher the stability of conjugate acid, better is the basic strength. So student, now a very important point I am going to talk about, that is the basic strength in gaseous phase or in gaseous solvent simply depends on electron density. More is the localization of electron, more is the localization of electron higher is the basic strength in gaseous phase. Simply you check electron donating groups are connected or not, localization of electron is there or not, electron cloud is available or not. Higher is the electron cloud available, higher is the electron density, more is the electron donating groups attached to this conjugate acid, higher is the stability of this conjugate acid, better is the basic strength in gaseous phase. So in gaseous phase, you simply need to talk about localization. More is the electron density, more is the electron cloud on the atom, higher will be the basic strength. I hope you understood basic strength in gaseous medium? Simply check whether the group connected is an electron donating group or electron withdrawing group. If it's an electron donating group, stability of conjugate will be higher, basic strength is going to be higher. I hope you understood. Let's move ahead. Now it's time to discuss basic strength in aqueous medium. Basic strength in aqueous phase. Mainly we talk about water. Basic strength if the solvent is water. I'm having a compound RNH2, right? It's taken in water itself. Water will behave as an acid. So what it will form? RNH3 positive, right student? This is the conjugate. Now here student, in aqueous medium, the basic strength depends on two factors: electron density factor, electron density factor, and the second one, solvation factor. You don't need to bother about all these two factors. We are going to discuss all these two factors in a detail after completing the basic strength in gaseous phase. Students, let's move ahead. Now let us talk about the basic strength across a period and down the group. Let's first of all talk about the variation of basic strength as we move from left to right across a period. Across a period, left to right. Student, as we move from left to right, we have studied that the atomic size decreases, but is the decrease significant? No. So if we move across a period, let us suppose I am moving from left to right in the second period, basically from carbon to nitrogen, nitrogen to oxygen, and oxygen to fluorine. No doubt there is decrease in size, but this decrease in size is not significant. Here the deciding factor is electronegativity. Electronegativity is the deciding factor, dominant factor. So now as we move from left to right, the electronegativity will increase. As we move from carbon to nitrogen to oxygen to fluorine, the electronegativity will increase. With increase in electronegativity, the donation tendency will decrease. So the basic strength will decrease. So as across a period, as we move from left to right, basic strength decreases. I hope you understood this one. Now let us talk about the basic strength as we move from top to bottom down the group. Let's talk about down the group case. Down the group. Now here how will you decide? Student, we have studied down as we move from top to bottom, or as we move down the group, the atomic size increases, and it increases significantly due to the addition of one extra cell, right? And here if I have to compare the basic strength, the dominant factor is stability of anion. Dominant factor, stability of anion. Now let's try to understand it with one example. I'm having F minus, Cl minus, Br minus, I minus. Which anion is more stable? Which is having higher tendency to accommodate this negative charge? Obviously I minus, because of larger size, because of higher atomic size, it can easily accommodate this additional electron cloud. This is more stable, and if it is stable, it will have less tendency to donate its electron cloud. Fluorine, being smaller in size, Chlorine being smaller in size, here the electron density will be very high. The charge density will be very high. So can I say the donation ability will be very high? So can I say the basic strength will be very high? So down the group, the basic strength decreases. Why it decreases? I hope you understood. Because down the group, as I move from top to bottom, the atomic size increases. With the addition of or with increase in this atomic size, this negative charge cloud or this additional electron cloud can easily get accommodated. So the stability of anion increases. With increase in the stability of anion, the donation ability will decrease, the basic strength will decrease. I hope you understood this one. Now let's practice some questions in order to understand it in a better way. Here, CH3 minus, NH2 minus, OH minus, F minus. All these species are the electron rich species. So they will behave as a base and they will have a tendency to accept protons. Right. We have to compare the basic strength. As we move from left to right across a period in the same period. Basically they are second period element. The electronegativity increases, the donation ability decreases, and the basic strength decreases. So CH3 minus is a better base as compared to NH2 minus, which is a better base as compared to OH minus, and F minus is relatively a weaker base as compared to CH3 minus. I hope you understood this one also. Let's move to the next question. This one just now we had discussed. Down the group, the basic strength will decrease. So F minus being a better base, then Cl minus, Br minus, I minus. This I minus is more stable, less donation ability. F minus less stable, higher charge density, more donation ability. Right? Next one. OH minus, SH minus. O, central atom O, central atom S. Second period, third period. Basically, we are moving down the group. The basic strength will decrease. So, which one is a better base? OH minus or SH minus? OH minus is a better base. CH3 minus, pH2 minus, SH minus, Cl minus. If I talk about these three elements, pH2 minus, SH minus, Cl minus, third period elements. And we are moving from left to right. As we move from left to right, the factor of electronegativity is the dominant criteria. Chlorine, highly electronegative, less donation ability. So between these three, can I say pH2 negative is a better base, then SH negative, then Cl negative. Now between CH3 minus and pH2 minus, obviously carbanions are a better base. Why? Because here one factor is the size factor, right? Phosphorus is having a vacant d orbital. It can accommodate the additional electron cloud or the additional electron in its vacant d orbital. So pH2 minus is more stable as compared to CH3 minus, right? And for a anion to be a better base, it should be highly reactive. It should be having high charge density. Then only it will have a tendency to donate at a faster rate or at a better rate, right? So CH3 minus is a better base. Let's move ahead. CH3 CH2 minus, CH2 CH minus, CH triply bonded C minus. Which one is a better base? What is the hybridization of this carbon? sp3, sp2, sp, right? Negative charge is present on sp, negative charge present on sp2 hybridized carbon, negative charge present on sp3 hybridized carbon. 25% S character, 33% S character, 50% S character. More is the percent S character, higher is the electronegativity. Higher is the electronegativity, lesser is the donation ability, lesser will be the basic strength. So which one is a better base? CH3, CH2 minus, then this one, and then this one, right? I hope you understood this one also. Let's move to the next question. Okay, This one. What is the hybridization of this base? sp2. Why? Because it's a neighbor of a sp2 hybrid carbon. So this negative charge will participate in resonance. So is the localization of electron? No. Basic strength is all about localization. More is the localized electron, more is the static electron, higher is the donation ability, higher is the basic strength. I hope you understood this one. Here this negative charge is delocalized. And this one is sp3 hybridized, no resonance, localized, fixed electron cloud. So can I say, since it is delocalized, it is participating in resonance. So here the electron density will be less. Lesser the electron density, lesser donation ability, lesser basic strength. So between these two, this one is going to be a better base. Next one. Once again, this negative charge is in resonance. And this one is also in resonance. So this one is also delocalized. Delocalized. And this one also in resonance, right? Delocalized. Now you only tell me where the extent of delocalization is more. Here students, it's in resonance with C double bond C. This one is in resonance with C double bond O. This C double bond O is a strong minus I and minus M group, right? So can I say here the extent of movement of this negative charge will be more, right? If the extent of delocalization is more, the basic strength is less. More is the delocalization, lesser the basic strength. More is the localization, more is the static electron cloud, more is the electron density, higher will be the basic strength. So this one is going to be a better base. Next one, OH minus, CH3O minus, C2H5O minus, and this one. Which one is a better base? Simply check electron density. Higher the electron density, higher the donation ability. Here hydrogen is there. Here plus I of methyl will operate. So because of the plus I of methyl, the electron density on oxygen will increase. The plus I of ethyl will operate. Because of the plus I of ethyl, the electron density on oxygen will increase. Here the plus I of terbutyl will operate. This one is having a better plus I, more is the electron donating group connected to anion, higher is the basic strength. So this one is a better base. Then we'll have ethoxide ion, methoxide ion, and then we have hydroxide ion. So students, always remember RO minus is a better base as compared to OH minus. Next one, CH2 minus, pH negative, right? We need to compare the basic strength. Here negative charge is present on sp2 hybrid carbon in case of this, right? Okay, here negative charge is present on sp3 hybrid carbon. In case of sp3 hybrid carbon, the percentage character is 25. Here the percentage character is 33. More is the percentage character, higher is the electronegativity, lesser is the basic strength. So this one is going to be a better base. I once again request you all, please copy it and do it on your own once again. Just copy the questions, don't look at the answers. Once again, do it on your own so that the concepts will be crystal clear. Let's move ahead now. Students, till yet mainly we were talking about the comparison of basic strength in gaseous solvent, mainly across the period, down the group. Then we had also discussed the comparison of basic strength of carbon ions. We had discussed how localization and delocalization of electron cloud affects the basic strength. Students, now it's time to discuss one of the most important organic bases, and that's mainly the compound of nitrogen. So now we are going to discuss nitrogenous base. These nitrogenous bases are basically classified in 4 different categories. First, aliphatic amines, aromatic amines, amides, and the last category is amidines. We are going to compare the relative basic strength of all these 4 classes of nitrogenous base. Let's discuss one by one. Aliphatic amines having a general formula RNHH2, right? Okay. So what's the hybridization here? sp3. So can I say, is the lone pair localized here? Localized lone pair. Lone pair, right, student? At the same time, I'm having a alkyl group connected. Minimum of one alkyl group is connected. So can I say this alkyl group will act as a plus I group, and this plus I will further increase the electron density. Already the electron cloud was localized, it was static. At the same time, this alkyl group attached to nitrogen acting as a plus I group, and it is increasing the electron density on nitrogen. Because of that, aliphatic amines are relatively a better base. If I have to compare between RNH2, R2NH and R3N in gaseous medium, basic strength simply depends on localization of electron, or it simply depends on electron density. Higher is the plus I group, more is the plus I, plus M, plus H group connected, better is the basic strength. So which one is going to be a better base? 1 degree amine, 2 degree amine, 3 degree amine? Tell me. 3 degree amine in gaseous medium, in gaseous phase. 3 degree amine is a better base. Then we have 2 degree, and then we have 1 degree. Now let's talk about aromatic amines. Aromatic amines are nothing but anilines. Okay. Now let's talk about this aniline. No doubt the lone pair is present here also. But what is the hybridization of this nitrogen? sp2. Right? So can I say this lone pair is used in resonance? It's in conjugation with the ring. So is it a localized or delocalized? Delocalized lone pair, right? So which one is a better base? Aliphatic amines or aromatic amines? Student, always remember, aliphatic amines is always a better base as compared to aromatic amines. Aliphatic amine is a better base as compared to aromatic amines. Why? In case of aliphatic amines, the lone pair is localized. In case of aromatic amines, the lone pair is delocalized. Now let's talk about the next two nitrogenous base. Amides. If I talk about the hybridization of this N, sp2, can I say this lone pair is also in resonance with this C double bond O group, and this C double bond O is an electron withdrawing group. Electron withdrawing group, what it will do? Can I say here the extent of delocalization will more? It will try to pull out this electron cloud. More is the extent of delocalization, lesser is the electron density, lesser is the basic strength. So now you have to compare. Tell me. Just close your eyes and tell me. Aliphatic amines, aromatic amines and amides. Which one is a better base? Aliphatic. Then aromatic amines. Then amides. The last one. Special category. Amidines. If I talk about this amidine, here you will say, so this lone pair is in resonance, right? And if this lone pair is getting delocalized, finally it will come here, right? So can I say the lone pair of this nitrogen is coming on nitrogen itself? So can I say the electron density on this nitrogen is increasing because of the plus M effect of this NH2 group? Yes or no? So can I say here on this nitrogen the electron density is very high, and higher is the electron density, higher is the basic strength. At the same time, here we are having one more thing, equivalent resonating structure. Because of that also the stability of conjugate will be more. So students, always remember, amidines are the most basic nitrogenous base. Then we have aliphatic amines, then we have aromatic amines, then we have amides. Amidines most, then we have aliphatic, then we have aromatic, that is aniline, and least basic nitrogenous compound is amide. amides are the least basic nitrogenous compound. I hope you understood this one. Let us move ahead. Compare the basic strength. Here we have to compare the basic strength in gaseous phase, gaseous solvent. Till yet we have not reached to aqueous solvent. Okay. In gaseous solvent, the basic strength simply depends on electron density. Higher is the electron density, better is the basic strength. NH3, hydrogen, 1 alkyl group plus I, 2 alkyl group 2 plus I, 3 plus I, in which case the electron density is more. 3 degree amines. So 3 degree amines in gaseous solvent is a better base as compared to 2 degree, then 1 degree, and then ammonia. The basic strength will vary like this. Next one. If I talk about this one and this one. Here, can I say this lone pair is delocalized? It's in resonance with the ring. If I talk about this one, what is the hybridization? sp3. And if the hybridization is sp3, can I say this one is a localized lone pair? Localized lone pair. Right? Okay. So can I say in the first compound the electron density will be more? So the basic strength will be more. Aliphatic amines, aromatic amines. Okay. Next one. We have to compare the basic strength of these compounds. I'm having NH2 group in conjugation with this S double bond O group, and this one is a very strong electron withdrawing group, right students? What this electron withdrawing group will do? It will pull out the electron cloud from nitrogen, so the electron density will decrease, and if the electron density will decrease, the basic strength will decrease. Here I am having C double bond O. Now which one is a better electron withdrawing group? SO2. Then this one. So if I have to compare the basic strength, amide is going to be a better base as compared to this one. Right? Now between this amide and aromatic amine, aniline, electron withdrawing group, here also resonance, here also resonance, but here the extent of resonance is more because of the presence of a strong electron withdrawing group. Here the extent of delocalization is relatively less. Here no delocalization, localization. Why localization? Because this nitrogen is sp3 hybridized. More is the localization, higher is the basic strength. Aliphatic amines, aromatic amines, amides, and then this one. So the basic strength, aliphatic amines, aromatic amines, amides, and this is going to be the least basic. I hope you understood this one also. Please copy it and then we'll move ahead. Let's move ahead now. We have to compare the basic strength here. I'm giving you 30 seconds each. Please do it. 30 seconds for this question and 30 seconds for this particular question. Now apply your logic, apply your brain, and do these two questions. Students, I hope and I believe you have solved this question. Now let's try to do it. Here, if I talk about the hybridization of this nitrogen, sp2. So can I say this lone pair is in resonance with this C double bond O and C double bond O? So can I say here two electron withdrawing groups are attached? So can I say the extent of delocalization will be very strong? So lesser the electron density on this nitrogen, lesser the electron density, lesser the basic strength. Here also it's sp2 hybridized, neighbor of sp2 hybrid carbon. If a lone pair or if an atom containing lone pair or negative charge is a neighbor of sp2 hybrid carbon, then that lone pair or negative charge is used in delocalization, right? And the hybridization is sp2. So this one is also sp2 hybridized, and this one will get delocalized. Here I am having one electron withdrawing group, C double bond O. Here two electron withdrawing group. In which case the extent of delocalization more? First one. Here less. So between 1 and 2, can I say here the electron density will be more? More is the electron, higher will be the donation ability, better will be the base. Now, between second and third one, here also, if I look at this particular compound, student, it's in resonance with this ring. At the same time, this one is also in resonance with this phenyl ring also, right? Here this lone pair was in resonance with only one. Here it's in resonance with two compound, one C double bond O and the other phenyl ring. So between 2 and 3, can I say still 2 is a better base? Why? Because here the extent of delocalization is going to be more. Now between 3 and 4, lone pair is in resonance with the ring, but this side there is no electron withdrawing group, right? So only delocalization. It's case of aromatic amines almost, right students? So can I say this one is aromatic amine and rest all are amides? Rest all these compounds are amides. This one is basically a sort of case of aromatic amines. Which one is a better base? Aromatic amines, right? So fourth one is going to be more basic. Then we will have between 1, 2 and 3, 2. Then we will have between 1 and 3. Here, no doubt here also, extent of delocalization is more because this lone pair is in resonance with the ring as well as in resonance with C double bond O. But here 2 C double bond O. Strong electron withdrawing group. So third is going to be a better base as compared to first and then 1. 4, 2, 3, 1. Next. Highly important. Most of the time such questions may appear in any of the competitive exam, whether it is JEE Mains, NEET or Advanced. Now, here can I say this lone pair is in resonance, and because of resonance the compound is aromatic, right students? So can I say because of aromaticity the extent of delocalization will be more here? Okay, here will this lone pair get delocalized? No, this lone pair is not there in pure p orbital. It is there in sp2 hybrid orbital perpendicular to the plane. So this lone pair is localized. And if I talk about this one, third one, once again delocalized, where the electron density is more in case of localization or delocalization. In case of localization, so second is going to be a better base. Now between 1 and 3, no doubt here also resonance is there and here also resonance in there, but in compound 1 aromaticity is achieved or attained because of this delocalization. So here the extent of delocalization is going to be more in case of pyrrole. Because of that the basic strength will be less. So 2, then 3, then 1. I hope you understood this particular question also. Let's move ahead. Students, now it's time to discuss the basic strength in aqueous medium. Okay, let's start our discussion. Let's start from the basic itself. I'm having a compound RNH2, right? Okay, it is reacting with an acid HA and it's forming a conjugate RNH3 positive, right students? Okay, and we have studied the basic strength of this compound will simply depend on the stability of this conjugate acid. Stability of conjugate. And how this conjugate will get stabilized? By attaching electron donating group to it, because here nitrogen is having a positive charge, electron deficiency, electron deficient species will always be in need or in search of electron donating groups. So can I say the stability of the conjugate will depend on first electron donating group attached to it, like plus I, plus M and plus H group, right? More is the plus I, plus M and plus H group attached to it, higher will be the stability of conjugate, better is the basic strength. One more factor, since my solvent is water, so what this water is going to do here, let's see. I'm having NH, positive H, and R, and I'm having my solvent water, H2O. Okay, lone pair, hydrogen, oxygen connected to nitrogen. What is the possibility here? Hydrogen bonding. And because of hydrogen bonding, which type of hydrogen bonding? Intermolecular hydrogen bonding. Now we know that bonding is exothermic process. So if hydrogen bonding will be there, energy will be releasing, right? Because of the release of the energy, can I say this conjugate will get stabilized further? So because of intermolecular hydrogen bonding, the stability of conjugate will be more, right? So there are two factors which decides the stability of this conjugate. The first factor is the simply electron density factor, and the second factor is solvation factor, or we can say solvation factor, or we can say hydrogen bonding, right? Now let us try to understand how solvation affects the basic strength. Okay, I'm having a compound CH3NH2. I'm having CH3NH, CH3, and then I'm having CH3N, CH3, CH3 lone pair. Okay, and we need to discuss the basic strength here in the presence of water, aqueous solvent. Aqueous solvent, perfect. Let's compare it. First, we have studied the basic strength in aqueous phase will depend on two factors, electron density factor and solvation factor. If I consider only electron density factor, first factor, electron density factor, then can I say because of the electron density, in this particular case I'm having maximum electron density, plus I, and plus I. Three plus I groups are connected here. More is the electron density, higher is the basic strength. So because of the electron density factor, can I say the order will be 3 degree amine, then we'll have 2 degree amine, and then we'll have primary amine, right students? The next factor, solvation factor. Okay, solvation factor. Let's form the conjugate and check solvation effect. CH3, NH3 positive, H positive, and I'm having CH3 NH, CH3 H positive. Okay, now what do you say? In which case I will have more extent of hydrogen bonding? Which one will get more solvated? So students, here I am having 3 acidic hydrogen. How many acidic hydrogen here? 2. More is the replaceable hydrogen, more is the acidic hydrogen, higher is the extent of hydrogen bonding. So in which case I will have better hydrogen bonding, more extent of hydrogen bonding. First one, 1 degree amine as compared to 2 degree. And if I talk about 3 degree, almost negligible hydrogen bonding here. And if I form the conjugate, only one acidic hydrogen, right, students? Okay. So can I say, if I consider solvation, 1 degree amine will have better solvation as compared to 2 degree, and 2 degree will have better solvation as compared to 3 degree. So if I consider solvation factor only, this 1 degree conjugate is going to be more stable. 1 degree more stable than 2 degree, more stable than 3 degree, right? But the basic strength or overall basic strength or overall stability of these conjugates will depend on both the factors. So after combining both these factors, the overall basic strength is 2 degree, then 1 degree, then 3 degree. If R is a methyl group. Okay, so if it is CH3NH2 group, then the order of basic strength in aqueous medium will be 2 degree, 1 degree, 3 degree. Student, if R is ethyl group like this, I'm having EtNH2, I'm having EtN, EtH, I'm having EtN, ET and ET. Then in this particular case, the relative order of basic strength will be 2 degree, 3 degree. Here the plus I effect will dominate over hydrogen bonding, and then we will have 1 degree. So you need to remember both these examples. Highly important. Students, now let us talk about the basic strength in case of substituted aromatic amines. And the first case which we are going to discuss is ortho substituted aromatic amines. Okay, I'm having aromatic amines. This one is nothing but aniline, right, student? Okay. Now here at ortho position, one group is substituted here. One group is substituted. Since it's the base, and the basic purpose of, or the main purpose of any base is to snatch acidic hydrogen or is to form sigma covalent bond. So this base NH2 is going to form a sigma covalent bond with hydrogen, and I will have this particular compound. This is nothing but conjugate acid. Conjugate acid, right, students? And we have studied the stability of conjugate acid will depend on electron density, and if hydrogen bonding is applicable, then also the extent of solvation or the extent of hydrogen bonding. Now, okay, I'm having NH3 positive, and at ortho position one group is substituted. Now when this water molecule will try to approach this conjugate, can I say it is going to face steric crowding or steric repulsion from this group G? And because of the steric repulsion, the extent of hydrogen bonding will decrease. And if the extent of hydrogen bonding will decrease, the stability of conjugate will decrease, or the basic strength of this ortho substituted aniline will decrease. So student, always remember, in case of aniline, if any group is substituted at ortho position, then irrespective of the nature of group, whether it is an electron withdrawing group or electron donating group, the basic strength decreases drastically. The basic strength will be less as compared to the para substituted or the meta substituted. So ortho substituted anilines are relatively a weaker base, or the basic strength is going to be very less. Even we say this effect as ortho effect, or we say it as SIP, steric inhibition in protonation. The protonation tendency decreases. Why? Because the intermolecular hydrogen bonding tendency decreases. Why? Because of steric crowding. Let's move ahead. Let's try to solve few questions related to substituted aromatic amines. The first question: aniline, ortho substituted aniline, meta substituted aniline, so it will act as a plus I. Here at para position I am having a methyl group, right? This methyl group acts as plus H and plus I, right? Okay. Delocalization, 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 delocalization. But here plus H and plus I group is attached. So can I say this para substituted aniline will be relatively a better base? Why? Because electron donating group is attached. So 4 maximum. Then between 2 and 3, here plus I is there. Here ortho effect is there, SIP. And because of SIP, the basic strength will be least. Even it is going to be less basic as compared to this aniline also. So now 4th maximum. Between 1 and 3, here plus I increases the basic strength. So after 4 I will have 3, then I will have 1, and then I will have 2. Ortho substituted anilines, least basic. I hope you understood this one. Let's move to the next one. Reference, nothing is there. Here minus I is there. Here minus I plus M is there, right? And here SIP is there. SIP. Ortho substituted aniline, least basic. So between 1, 2, 3, 4, can I say 4th is going to be the least basic? Then here minus I. Here at least minus I is there, but at para position, and at para position this minus I is relatively very so 4th is going to be the least basic. Now between 1, 2 and 3, no electron withdrawing group, nothing. So can I say between 1 to 3, 1 is going to be the most basic? No, between 2 and 3, minus I, minus I. At the same time a weak plus M is also there. At the same time, one more thing, minus I at para position, relatively very weak effect. So between this meta substituted and para substituted, this para one is going to be more basic. So 1, 3, then we will have 2, and 4th one is going to be the least basic student, right? Let's move to the next question. Please do it. Moving to the next question which we have, I hope you have done it. So moving to the next question which we have on the screen, and the question is NH2 ortho substituted, meta substituted, para substituted. Can I say here plus M effect is there, minus I effect is there, SIP is there? Nothing. Plus M, highly electron donating group, right, increases the basic strength. So can I say 4th is going to be the most basic? SIP, least basic. 2nd is going to be the least basic. Between 1 and 2, 1 and 3, here minus I, here nothing. So 4, after 4, 1, then this minus I 3rd, and 2nd because of SIP is going to be the least basic. Simply you need to check which electronic effect is operating. If it's a plus I plus M plus H group, basic strength will increase. If it's minus I minus M minus H group, basic strength will decrease. If it's SIP, the basic strength will decrease to a higher extent. Let's move ahead. Next one, SIP. Irrespective of the nature of the group, I will simply write SIP here. Minus I minus M. Reference. Okay. In every case, we have electron withdrawing group. Nothing. So 4th one is going to be maximum. Then we will have minus I. 2nd one. Then we will have minus I minus M. 3rd one. And the least one is going to be the first one. because of SIP. The next one, student, this one is also quite important. Here the lone pair is localized. We have discussed this case, pyridine. This one is pyrrole and this one is aniline, which is more basic. Aniline, pyridine and pyrrole. Pyridine, because in pyridine the lone pair is localized. So this nitrogen is more basic. Let's number it as 1. This one is 1, 2 and 3. So can I say 1 is more basic? Now between this aniline and pyrrole nitrogenous compound, this 2 is going to be more basic, because here no doubt delocalization is there, but here because of delocalization the aromaticity is achieved, so extent of delocalization is more. So 1, then 2 and then 3. I hope you understood this order also. Let's move to the next one. Can I say SIP is operative here? Okay, and because of SIP the basic strength will be very less. Now I will say, sir, SIP may also operate here. No, student, here basically I'm having 2 methyl group connected to this nitrogen. At the same time I'm having steric crowding or blocking at ortho position also. Because of that here SIR effect is operative, steric inhibition in resonance, and because of SIR this lone pair will get localized. It will be localized lone pair. Localized lone pair. And if it's a localized lone pair, can I say the basic strength will be more? More is the localization, higher is the basic strength. So this one is a better base. Please copy it. Students, now let's try to understand a very important concept, and that is amine flipping. How does it occur? Let's try to understand, and how it impacts the basic strength or affects the basic strength. Let us try to understand. I'm having a acyclic amines. Acyclic amines. This phenomenon is observed only in case of acyclic amines, not in cyclic nitrogenous base. Okay, so what happens? I'm having RNH2. If I look at the structure, it will have a structure like this: N R H H, one lone pair, and this lone pair is a localized lone pair, right? It's fixed. Now since it's fixed, after certain time what will happen? Because of this localization of electron density, some strain will develop, and in order to release the strain, this acyclic ammonia or this acyclic amines undergo flipping process. The flipping is just like when you go in a stormy weather and you take an umbrella, or if you hold an umbrella, first the umbrella shape is like this. After a certain time it will become like this, and then it will become like this. The same situation is here also. This particular state is nothing but intermediate between these two. So this is the transition state. So in this amine flipping also, we get a transition state where we achieve planarity. The molecule becomes like this, and then we will have a lone pair here. This is the transition state, TS. And finally, what happens? I will have a structure like this. This lone pair will come down, and these hydrogens H and R will come up like this. And this flipping occurs at a very, very faster rate. This process is highly reversible. 1 and 2. This is a highly reversible process. And in between, we achieved a transition state in which the hybridization of nitrogen is sp2, or we can say planarity is achieved. And if planarity is achieved, the hybridization becomes sp2. And if the hybridization becomes sp2, the percentage character will increase. Because of the increase in the percentage character, the basic strength will decrease. So students, in case of acyclic amines, we always observed amine flipping, or because of this amine flipping, the basic strength decreases. So acyclic amines are always a weaker base as compared to a cyclic amines. I hope you understood this amine flipping process also. Let us try to solve this particular question. I'm having 3-degree amine, aliphatic amine, aliphatic amine, aliphatic amine. The first one is acyclic, open chain. These two are cyclic. In cyclic amines, we don't observe amine flipping, right? We can't have flipping. There is restriction in rotation. If the flipping will occur, then this bond will break. So in case of cyclic amines, there is no flipping process. Now, can I say these two compounds will be a better base as compared to the first one? Because here in the TS, I'm having sp2 hybridization, more percent S character, more electronegativity, lesser donation ability. So this one is always a weaker base as compared to these two. Now if I have to compare between these two, here carbon is there, here oxygen is there. Oxygen is the electron withdrawing group, right? So because of induction, the electron density will get somewhat reduced, and this reduction in electron density will decrease the basic strength. So between 2 and 3, which one is a better base? 2. So the relative basic strength order 2, then 3, then 1. Right, students? I hope you understood this amine flipping process also. Students, that was all about the basic strength of organic compound. I hope you understood how to compare the relative basic strength of organic compound. Students, now it's time to discuss one of the most important topic of this reaction mechanism, or one of the most important subtopic, that is nucleophile and nucleophilicity. Let's discuss about that. What do we mean by the term nucleophile? Nucleo stands for nucleus, and nucleus are positively charged species. Phile stands for lover, lover of positively charged species. Which one is going to be the lover of positively charged species? All the electron rich species. So can I define nucleophile as the electron rich species having a tendency to form sigma covalent bond with electron deficient species, right? And all the electron rich species which is having a tendency to form sigma covalent bond with electron deficient species. Now which all species can be electron rich species? All the anionic species, right? All the anionic species will be electron rich species, right? Can we have few examples? H minus, R minus, OH minus, SH minus, Cn minus. Can I say all these species will behave as a nucleophile, right? Okay. Apart from this, even few neutral species also, right? So which all neutral species may behave as a nucleophile? All the species having lone pair, then only it will have a tendency to donate a pair of electrons, right? So if I talk about neutral nucleophiles, then we can have the examples NH3, H2O, H2S. Everywhere I am having lone pair, right? RNH2. Okay, so these are also having nucleophilic behavior, right? All the nitrogenous compound, water, H2S, they are having the nucleophilic behavior. Apart from these, we are having few more examples of nucleophiles. Neither they contain negative charge nor they contain lone pair, still they are having a nucleophilic behavior. Can you name them? Yes, the neutral species like alkene, RCH doubly bond CH2, alkene, alkyne, benzene, In all such cases, I am having loosely bound pi electrons, right? Pi bond is basically formed by the lateral overlap. So this lateral overlap is relatively weaker. So it is a loosely held pi electron. So these species also behaves as a nucleophile, right? So all these electron rich species are nothing but nucleophile. Now you will say, so you told the same thing in case of base also. They are also the electron rich species, right? And having a tendency to donate pair of electrons. Then what's the basic difference between, or what's the main difference between a nucleophile and a base? Let us try to understand it. I'm having species like this: R, CH, CH2 positive, and here one CH. Okay. Now I'm taking two electron rich species, one Nu minus and one B minus. This B minus is indicating the basic behavior of the electron rich species, and this Nu minus is indicating the nucleophilic behavior. Nucleophilic behavior, and this one is having a basic behavior. Now, what is the function of base? To snatch acidic hydrogen, to form a sigma covalent bond with hydrogen. So what this B minus will do? It will snatch this hydrogen. Why? Because this hydrogen is acidic, alpha hydrogen. Alpha hydrogen. So this, this electron rich species is having a basic behavior, it is going to snatch this hydrogen and will form a compound BH. As soon as this hydrogen will get removed in the form of H plus, I will have a negative charge, and the product formed will be RCH doubly bond CH2, right? So this B minus will form alkene when it reacts with this carbocation. Now, if the electron rich species, this Nu minus, is having a nucleophilic behavior, then what it will do? It will simply attack and will form a sigma covalent bond with this electron deficient species carbocation. It is simply going to form sigma covalent bond with this carbocation. And what will be the product formed? R CH2 CH2 Nu. So what's the function of nucleophile? To form a sigma covalent bond with any electron deficient species other than hydrogen. Then this electron rich species will behave as a nucleophile. If the electron rich species snatches H plus, then that electron rich species will have a basic behavior. Now which reaction will occur at a faster rate, or which one is more spontaneous? A acid base reaction is always faster and spontaneous as compared to other reactions, right? Okay, so first, a electron rich species will have a basic behavior. If there is no acidic hydrogen, then it will have a nucleophilic behavior, students. I hope you understood this one also. Let's move ahead. Students, while talking about basic strength, we have discussed a very important terminology, basicity. Simply here, we are going to discuss nucleophilicity. Basicity is all about the relative tendency to form sigma covalent bond with H plus. Here, it's the relative tendency to form sigma covalent bond with any electron deficient species other than H plus. Let's write it. The relative tendency to form sigma covalent bond with any electron deficient species, any electron deficient species other than H plus. Okay, so it will simply form sigma covalent bond with any other electron deficient species. Now one more important point. Here nucleophilicity is all about speed. Nucleophilicity is a kinetically controlled process. Here, what do we mean by the term kinetically controlled process? It simply means how faster it forms a sigma covalent bond with electron deficient species. Nucleophilicity simply depends on speed, how fastly it attacks or how fastly it forms a sigma covalent bond with a electron deficient species. Let us try to understand it like this. I'm having an electron deficient species E plus, and now I'm having two electron rich species Y1 minus, Y2 minus. If it is having a nucleophilic behavior, what it will do? It will simply attack here and will form a sigma covalent bond. Let us assume the time taken by this Y1 minus to attack on E plus is 2 seconds. And the time taken by this Y2 minus to attack on this E plus is 3 seconds. Which one is attacking at a faster rate? Y1 minus. So which one is a better nucleophile? Y1 minus. Y1 minus better nucleophile as compared to Y2 minus. I hope you understood what do we mean by kinetic control process. Here it's all about speed. Now, student, let us try to talk what are the factors which impact the nucleophilicity of a compound. Nucleophilicity of a compound, nucleophilicity of compound depends on 4 factors. Compound depends on 4 factors. First one, charge. Highly important. Charge. Second one, electronegativity. Electronegativity. Third one, steric crowding. Steric crowding. Fourth one, solvation. We'll discuss all these factors one by one. Let's first focus on charge. Charge factor. Charge factor. Student, if the donor atom is same, let us understand it like this. I'm having H2O and I'm having OH minus. Obviously in both the case the donor atom is oxygen, right? Now if the donor atom is same, higher is the charge density, better is the nucleophilicity. Let's write it. If donor atom is same, highly important, please write it. If donor atom is same, higher the charge density, better is the nucleophilicity. Nucleophilicity, or we can say nucleophilic strength. Right? Now, donor atom is oxygen in water. In OH minus also the donor atom is same, right? In which case do we find more charge density? Here, right student? So we can also say anionic species is always a better nucleophile as compared to a neutral one. I can have this one, NH3, NH2 minus. Which one is a better nucleophile? This NH2 minus. H2S, SH minus. Which one is a better nucleophile? This SH minus. So always if the donor atom is same, higher the charge density, higher is the nucleophilicity. One more thing, I'm having OH minus, RO minus. In which case do we find more charge density? This alkyl group will increase the charge density on oxygen. Donor atom, same oxygen, oxygen. In case of alkoxide, the charge density is more. So this one is a better nucleophile. I hope you understood the first factor, right? Very simple. Let's move to the next one. Electronegativity factor. Electronegativity factor. This factor mainly we see across a period. Across a period, as we move from left to right, as we move from L to R, electronegativity will increase, and if electronegativity will increase, the donation ability will decrease, the nucleophilicity will decrease. Okay, but always remember, this factor is only considerable when the size is almost similar, right? So if the elements are belonging to the same period, then only will apply this concept. This factor of electronegativity will only be applicable if all the elements are belonging to the same period. Let's try to take one example. I'm having CH3 minus, NH2 minus, OH minus, F minus, right? Second period element. Now, as I move from left to right, the electronegativity increases, the donation ability will decrease, the nucleophilicity will decrease. This one is a better nucleophile. I hope you understood this factor also. Let's move to the third factor. Steric crowding. Student, already I told you, nucleophilicity simply depends on speed. How faster it attacks on the electron deficient species. Now, simply you tell me. No doubt donor atom is same. In this particular case, the charge density is higher. Charge density is more. In case of terbutoxide ion, right? Terbutoxide ion charge density is more. You will say, sir, if the donor atom is same, charge density is more, so donation ability will be better, nucleophilicity will be better. But I told you in the beginning only, nucleophilicity also depends on speed, how readily it attacks. Here, because of the bulkiness, the relative speed will be less. So terbutoxide ion, no doubt, having higher charge density, but still a weaker nucleophile as compared to ethoxide ion. Right, students? I hope you understood this one also. More is the steric crowding, lesser is the nucleophilicity. Students, now let us discuss the effect of solvent in case of nucleophilicity. How solvent affects nucleophilicity. First, let's talk about solvent. We'll do a brief discussion about solvent. Okay. If I talk about the solvent, they are of two types. One, polar. The other one, non-polar. Right? If I talk about non-polar solvent, the dipole moment here is 0. Right? They are basically the symmetrical molecules like CCl4, organic solvent, N-hexane, CH2, all these are non-polar solvent. Toluene, benzene, right? Toluene, all these solvents are non-polar solvents. Now if I talk about the polar solvent, it's divided in two categories. Polar, protic, and the next one is polar aprotic. If I talk about polar protic solvent, already if the solvent is polar, means dipole moment is non-zero, right? Now if I have to talk about polar protic solvent, the polar solvent which is having acidic hydrogen, right? Where the hydrogen is connected to a highly electronegative element. All the solvent which is having a tendency to release protons like water, polar protic solvent, alcohol, ROH, RSH, right? So students, these solvents are polar protic solvent. Now if I talk about polar aprotic solvent, no doubt the dipole moment is non-zero, but they don't have acidic hydrogen. The dipole moment is still here non-zero, but they don't have acidic hydrogen. The best example is acetone. Do you find any acidic hydrogen? Here the hydrogen is connected to carbon. We have DMSO, dimethyl sulfoxide, DMSO. We have ether. All these solvents are polar aprotic solvents, right? So I hope you understood what is solvent, what are the different types of solvent that we have to study. Now let us talk about the effect of solvation in case of nucleophilicity. Okay. Students, I'm having a nucleophile X minus, right? Now this X minus is taken in a polar protic solvent, H2O. Can I say, smaller the size of anion, smaller the size of X minus, higher will be the charge density. Higher will be charge density because charge upon volume. Volume is small, charge is higher. Can I say charge density will be more? So smaller the size of atom, higher will be the charge density. Charge density, and if charge density is higher, solvation is directly proportional to charge density. Charge density simply depends on size of atom. Smaller the size of atom, higher will be the charge density. So can I say, if this X minus is more, it will get more solvated. How the solvation will occur? Let us try to understand. I'm having X minus, it is taken in a polar protic solvent. What this water will do? It will surround, and this water is having acidic hydrogen, del H plus, H, O, H, once again acidic hydrogen. Can I say there will be a physical bond formed between these elements, right? So smaller the size of this particular ion, higher is the charge density, and higher the charge density, more and more water molecule or more and more solvent molecule will surround it. And if more solvent will surround it, can I say, because of physical bonding, the size of ions will increase. The steric crowding will increase around this solvent. And because of this increase in the steric crowding, can I say the nucleophilicity will decrease. Right, students? So, in case of polar protic solvent, smaller the size of ion or anion, better, more is the solvation, lesser is the nucleophilicity, right? So if I'm having F minus, Cl minus, Br minus, I minus taken in water, which solvent? Polar protic solvent. In this case, what is going to be the nucleophilicity order? I minus, better nucleophile, Br minus, Cl minus, F minus, more solvation, less nucleophilicity, right? So in case of polar protic solvent, the nucleophilicity will increase down the group. Now In case of aprotic solvent, in case of aprotic solvent, now here we don't have any solvation effect. Here nucleophilicity will depend on charge density. Nucleophilicity depends on charge density. Where do you find more charge density? F minus or I minus? The one having higher size will have smaller charge density. F minus being smaller in size will have higher charge density. Higher is the charge density, more is the nucleophilicity. So in aprotic solvent, F minus is a better nucleophile, then Cl minus, then Br minus, then I minus. This one in case of ether. If ether is a nucleophile, then, sorry, if ether is the solvent, if DMSO is the solvent, if acetone is the solvent, then F minus is a better nucleophile, then Cl minus, then Br minus, then I minus. Student, I hope you understood the effect of solvation and how solvation impacts nucleophilicity. Let's move ahead. So students, now let us compare nucleophilicity and basicity of certain electron-rich species. The first one, I need to compare nucleophilicity and basicity of these two compounds, right? The nucleophilicity, first of all, can we say these elements belongs to second period? They are second period element, right? And here I am moving from left to right. If the donor atom is from the same period, then the dominating criteria and the factor which decides nucleophilicity and the basicity is electronegativity. As we move from left to right, electronegativity increases, the donation ability will decrease, right? So the nucleophilicity and basicity will remain same for these compounds, right? Donor atom belongs to the same period, nucleophilicity and basicity will remain the same. Same story in case of SiH3 minus, pH2 minus, SH minus, Cl minus, third period elements. Once again, the deciding factor is electronegativity, right? As I am moving from left to right, electronegativity is increasing, the donation ability will decrease, both nucleophilicity as well as basicity will decrease as I am moving from SiH3 minus to Cl minus. Which one is more nucleophilic? SiH3 minus. Which one is more basic? SiH3 minus. Next one, F minus, Cl minus, Br minus, I minus. I need to compare nucleophilicity first of all. We have seen in case of polar protic solvent, as we move down the group, the size of ion increases, right? The charge density decreases. Because of that, solvation decreases and nucleophilicity increases. So in a polar protic solvent, which one is a better nucleophile? F minus or I minus? I minus is a better nucleophile. In polar aprotic solvent, which one is a better nucleophile? F minus is a better nucleophile. So this was all about nucleophilicity down the group. Now let's talk about basic strength. Student, basic strength simply depends on charge density. Higher is the charge density, more is the localization of electron cloud, better is the donation ability, higher is the basic strength, right? So as I move from top to bottom or as we move down the group, the basic strength will decrease. So basicity order, F minus, Cl minus, Br minus, I minus. F minus is a better base. In a group, the nucleophilicity increases while basicity decreases on moving top to bottom. But here, if I am talking about this nucleophilicity, basically I am talking about polar protic solvent, right? I hope you understood this one also. Let's move ahead. OH minus and SH minus. Which one is a better base first of all? Obviously, OH minus. OH minus will have higher charge density. In case of SH minus, negative charge is present on sulfur. In case of sulfur, I am having a vacant 3d orbital, more stable, less donation ability. Right? So both nucleophilicity as well as basicity will be better for OH minus. Right? We can understand the basic strength like this also. OH minus base. So conjugate acid H2O, right? SH minus base, conjugate acid H2S. Now between H2O and H2S, which one is a better acid? H2S is a better acid, right? So if conjugate is a better acid, then the parent base will be a weaker base, right? If conjugate is going to be a better acid, or we can say H2S stronger acid as compared to H2O, so the conjugate of H2S is SH minus will be a weaker base as compared to OH minus. In a simpler word, okay, I'm having RO minus RS minus, right students? I need to talk about the nucleophilicity. Students, RS minus is a better nucleophile as compared to RO minus. Please keep it in mind, this one. And if I talk about basic strength, the order is reverse. RO minus is a better base as compared to RS minus. RO minus is a better base as compared to RS minus, but RS minus is a better nucleophile. This one is a very good nucleophile. Now, RO minus and OH minus. Here, the donor atom is same. Simply the nucleophilicity and basic strength will depend on charge density. Higher is the charge density, more is the donation ability. Here, alkyl will act as a plus I group. The charge density will increase. The basic strength will be more. If the donor atom is same, nucleophilicity and basicity have almost the same order. Okay. I'm having RCOO minus, PHO minus, HO minus, RO minus. I need to compare nucleophilicity as well as basic strength. Student, in case of RCOO minus, I'm having symmetrical equivalent resonating structure. Because of delocalization of negative charge, the electron density will be less. In PHO minus also we will have resonating structure, but this RCO minus is more stable as compared to PHO minus. More is the stability of ion. Once again I am saying this very important statement. Please listen to me very carefully. More is the stability of anion, lesser is the basic strength. Why? More is the stability of anion, lesser will be its tendency to donate. Because in anionic form itself it's stable, and if it is stable it will have least tendency to donate, right? So higher the stability of anion, lesser is the basic strength. Between RCO minus and PHO minus, RCO minus is more stable, carboxylate anion is more stable as compared to phenoxide ion. So carboxylate ion will be a weaker base, a weaker nucleophile as compared to phenoxide ion. Now in these two cases, OH minus and RO minus, we have already studied RO minus, more charge density, more nucleophilicity as well as basic strength. I hope you understood these things, student. Let's move ahead. I'm having RCO minus R, S double bond O, double bond O, O minus. Which anion is more stable? This one. More is the stability of anion lesser is the basic strength. Okay. OH minus H2O. More is the charge density, higher is the basic strength as well as nucleophilicity. Neutral nucleophiles and anionic nucleophiles. Anionic nucleophiles are always a better nucleophile because of high charge density. We have discussed these things, right? Now this one. CF3 SO3 minus, PHCOO minus, PHO minus, OH minus, RO minus, the nucleophilicity and basic strength. In these two cases, we are having resonance stabilization, even here also. So till here, because of resonance, these anions are highly stable anions. So they are very weak nucleophile, weak base. In all such cases where I am having resonance, such anions are relatively weaker nucleophiles as well as weaker base, because those anions are more stable, and higher is the stability of anion, lesser will be the tendency to react, lesser will be the donation ability, lesser is the basic strength, lesser is the nucleophilic strength. These two anions are good nucleophile as well as good base. I hope you understood this one. Let's move ahead. So student, till yet mainly we had discussed basic strength, right? Basicity, nucleophilicity, nucleophilic strength. Now we are moving to the third topic, subtopic of today's class, and that is leaving ability of leaving groups. Let's try to learn this particular concept also. Although once again it is similar or repetition of the previous two concepts. The same concepts we are going to discuss here also, but it in a different way. Okay. Let's talk about the leaving ability of a leaving group. You might have studied several reactions like substitution reactions, elimination reaction, where one of the group has to depart, right? I'm taking a substrate RLG, and let us assume here substitution reaction is occurring. I'm having an electron rich species Nu minus. It is coming, is attacking over here, and then this group is departing. Now, as soon as this group is departing, basically it will depart in the form of Lg minus. So it generally leaving group departs as anionic species. Anionic species, right? Okay. Now if it is an anionic species, means it is having a basic behavior. Basic behavior, right? I hope you understood this one also. Now, can I say the leaving ability of this leaving group will depend on the stability of Lg minus? It will only depart at a better rate when this Lg minus is more stable. Let's write it. Leaving ability of a leaving group simply depends on stability of Lg minus. Okay. Now, if this Lg minus is stable, this Lg minus is having a basic behavior, but it is stable also. So if it is stable, will the basic strength be more or less? Obviously, if the anions are stable, the donation ability will be less, the basic strength will be less. So can I say leaving ability is inversely proportional to basic strength. Basic strength. Right, student? Simple one thumb rule. Whenever you are asked to compare the leaving ability of leaving group, simply either check the stability of anion, check which all electronic effects are operating, or you can do one thing, simply compare the relative basic strength. You have studied the basic strength now. You can easily do it, right? I hope you understood this. Leaving ability of a leaving group inversely proportional to basic strength. Students, now on the basis of leaving ability, we classify leaving groups into three different categories. Very good leaving group, moderate leaving group, and poor leaving group. Let's talk about that. First one, very good leaving group. Very good leaving group. Good leaving group. Such living groups does not need any external reagent for departure. It departs as soon as it is dissolved in any solvent. The examples of such living groups may be: first, N2 positive. We have studied diazonium, right? Rn2 positive. So this one, it will get departed in the form of nitrogen, right? As soon as it departs, basically we are getting nitrogen, highly stable molecule. And living ability simply depends on the stability of the living group after departure, right? Okay, next one. I'm having tosylate iron. This structure is very important. The name is tosylate. Next one, triflate. Double bond O, O minus. Next one, nitrosylate. S double bond O, O minus NO2. H2O positive. H2S positive. Right? These species are very, very good living groups. Now let's talk about moderate living groups. Moderate living groups. We have studied this one. What's the name of this particular compound? Alkyl halide, right? Now here, this halogen will get departed in the form of X minus. Now this X minus is relatively a moderate type of nucleophile. Now the living ability here also will depend on the stability of X minus between Cl minus, Br minus and I minus. Cl minus, Br minus, I minus. What do you say? Which one should be a better living group? The one which is more stable, or the anion or the Lg minus which is more stable after departure is a better living group. Or we can compare on the basis of basic strength. Cl minus and I minus, which one is more basic? Cl minus. So Cl minus will have a weaker living ability as compared to I minus. I minus, more stable, better living ability. Now we will say, sir, why not you have written F minus? Students, F fluorine after departure gets converted to fluoride ion, and this fluorine is a very, very poor living group, right? It's very tough to remove fluorine in the form of fluoride ion because of high electronegativity, right? Fluoride ion, if I compare here also, F minus and I minus. F minus is a strong base as compared to I minus. So the one which is a strong base will be a poor living group, right? Okay, the third one, poor living group. Poor living group. Such living group even cannot be departed by external reagent. Such living group requires internal nucleophile or internal reagents. Basically, if I talk about the poor living group, we have 2 to 3 different groups. OH minus, RO minus. Can we say they are a strong base? And a strong, if it is a strong base, then it is a poor living group, right? Apart from this, we are having F minus also. So these three are poor living group. Halide ions, mainly chloride ion, bromide ion, iodide ions, are moderate type of living group. Tosylate ion, nitrosylate ion, brosylate ion, triflate ion, N2O, Rn2 positive, RH2O positive, RH2S positive. Such living groups are the best living groups. I hope you understood this one. Please complete. Now students, it's time to practice few questions on the basis of living ability of living group. CH3 minus, NH2 minus, OH minus, F minus. What do you say? Which one is a better living group? Simple, here we can compare the living ability on the basis of basic strength. Basic strength. More is the basic strength, poor is the living ability. More is the basic strength, poor is the living ability. CH3 minus being a better base, so it will have the worst leaving ability. Leaving ability will be like this. RO minus RS minus. What do you say? Which anion is more stable? Here the sulfur is having a vacant 3D. It can easily accommodate the electron cloud. So this one is more stable, right? Now, NH3, H2O and N2. Between ammonia and water, which one is a stronger base? Ammonia. So can I say ammonia will be a poor leaving group? So between water and ammonia, obviously, water is going to be a better leaving group. Ammonia is stronger base, weaker leaving group. Now, between water and nitrogen, what do you say? Between water and nitrogen, this one is relatively more stable, right? So the leaving ability will be like this. I hope you understood this one also. Let's move ahead. F minus, Cl minus, Br minus, I minus. Leaving ability simply depends on the stability of anion. Leaving ability simply depends on the stability of anion. I minus more stable, then Br minus, then Cl minus, least stable, lesser leaving ability. RO minus, OH minus, RC double bond O minus, and here. Can I say here I will have symmetrical equivalent resonating structure. Even here also. Now between 3 and 4, which one is more stable? This one. So can I say the leaving ability will be like this? Between these two, more is the stability, lesser the basic strength, higher is the leaving ability of anion. Now between these two, OH minus and RO minus, this one is a stronger base, so this one will be a better leaving group, right? Now between OH minus and RC double bond O minus, obviously this one is more stable. More is the stability of anion, better is the leaving ability. Let's move to the next question. CH3COO minus, CF3COO minus. The group is same here. Now here I am having an electron withdrawing group, minus I group, plus I group. The charge density will be more, stability will be more. More is the stability of anion, higher is the leaving ability. This one, OTS, it's referred as OTS. In most of the question, while solving or practicing, you will see in books, they simply give you OTS. This is OTS, nothing but tosylate iron. Okay, this one simply pH S double bond O, S O3 minus, brosylate, nitrosilate. What do you say? Which one is more stable? If I look here, in every case I am having SO3 minus is in resonance with the ring. Every case. Here CH3 plus I plus H group will destabilize the anion. Reference group minus I group and plus M group, but very weak plus M group. Minus I minus M group, very strong minus I and minus M. So can I say this particular anion is going to be the most stable one, right? Okay, now between, if I need to compare 1, 2 and 3, can I say the leaving ability will be like this? And here also, right? Here reference, here plus H, plus I group will destabilize the anion. Lesser the stability, weaker the leaving ability, right? We have discussed this one, ammonia, water and N2 just now. I hope you understood the leaving ability of leaving group. Student, you need to simply learn one thing. Leaving ability directly proportional to stability of anion, inversely proportional to basic strength. Inversely proportional to basic strength. That's it, all about leaving ability of leaving groups. First reaction, that is nucleophilic substitution reaction. The name itself says substitution, right? So I will have a substrate like RLG. I will have an incoming nucleophile. What this nucleophile will do? It will attack here. The leaving group will depart and simply the nucleophile will substitute the leaving group, right? Now, student, although this reaction seems so simpler, but we have different mechanisms through which this substitution reaction can occur, right? It is a possibility that the nucleophile and the leaving group, the attack of nucleophile and departure of leaving group occurring at the same time. It is also feasible that the leaving group first departs and then the nucleophile attack, right? So we are having different feasibility. On those feasibility, we will have different mechanisms and will have different pathway. So let us talk about the different types of nucleophilic substitution reaction which is there in our syllabus. First one, Sn1 reaction. S substitution and nucleophilic 1 unimolecular. Sn1 stands for unimolecular substitution reaction. We'll talk about this. Don't worry. Highly important reaction pathway. Second, Sn2. S substitution and nucleophilic substitution reaction bimolecular. 2 molecules, 1 molecule. Then third one, Sn I stands for intramolecular. So intramolecular nucleophilic substitution reaction. Fourth one, Sn NGP. NGP stands for neighboring group participation. We also say it as anchimeric assistance. Don't worry, we'll discuss about that also. We have one more type of Sn reaction, although we'll discuss this Sn reaction in case of alkyl and aryl halides, but let's write the name SnAe or SnEA. A stands for addition, E stands for elimination. Nucleophilic substitution, addition, elimination reaction, and the second one is nucleophilic substitution, elimination, addition reactions. So these are the different pathway through which the nucleophilic substitution reaction will occur. Let's discuss one by one. Unimolecular nucleophilic substitution reaction, Sn1. Highly important. Let us try to understand it. Student, basically such reaction occurs in 2 steps. I'm having a substrate RLG, right? It is treated with a polar solvent, or mainly we can say polar protic solvent. What will happen? The ionization of the leaving group will occur. I will have the formation of carbocation as an intermediate, and in the second step the role of nucleophile will come. Now this nucleophile will attack and I will have the formation of RNU. Don't worry, we'll discuss in a very detailed way. The first step, ionization of or the departure of leaving group to form carbocation. And the student, here can I say in the first step basically the leaving group is departing, so a neutral species is getting converted to a charged one, right? I'm having a substrate RLG, or we can have alkyl halide. This halogen gets departed in the form of halide ions, and I'm having a formation of carbocation. Student, always remember, whenever a carbocation is formed, the formation of carbocation always occurs at a very slow rate. So this particular step is going to be the slowest step of the reaction, and the slowest step is referred as rate determining step. We talk about the rate of reactions on the basis of RTS itself, right? Second step. Now I'm having a carbocation. On this carbocation the nucleophile will come and will attack, right? Charged species reacting with Nu minus, forming a neutral species. Obviously this reaction is going to be, the second step is going to be relatively faster, right? So second step, a fast step. I'm having carbocation, nucleophile attacks over here, and I will have the formation of my product. Now let us try to understand the mechanism of this particular reaction in a better way. I'm having an alkyl halide, you can see here, right? 3 carbon. The first step, ionization of alkyl halide or ionization of substrate, and this particular step is initiated by a solvent. Mainly the solvent taken is polar protic. What this solvent will do, it will try to ionize this Rx bond. Okay, now in the first step I will have the ionization, I will have the departure of the leaving group, and this step is initiated by a solvent. That's why Sn1 reaction is also referred as solvolysis reaction. Sn1 reaction is also referred as solvolysis reaction. Why? Because Sn1 reaction is initiated, it's catalyzed by a solvent itself. So now I will have a formation of carbocation. What's the hybridization of carbocation? sp2, right student? And if it is sp2 hybridized, can I say the molecule is going to be a planar molecule? sp2 hybridized species are planar. Now I am having nucleophile. On a planar molecule, nucleophile can attack from both the sides, front side as well as from back side. So how many products I am going to get? 2 products. And these 2 products will be mirror image of each other, right? Sn1, once again I am repeating. First step, ionization by a solvent, formation of carbocation. This first step is going to be the rate determining step. It occurs at a very slow rate. Once the carbocation is formed, it may undergo rearrangement. Whenever there is a formation of carbocation always undergo rearrangement to give more stable carbocation. And once I have the formation of a more stable carbocation, then on this most stable carbocation, nucleophile will approach from the front as well as from the back. How many products I will get? 2 products. And these 2 products will be mirror image of each other, right? And if they are the mirror image of each other, and if it is optically active, we'll have enantiomeric pairs. In that particular case, we may have racemization or we may get racemic mixture, right? Carbocation intermediate is formed, so rearrangement is feasible in Sn1 reaction. Whenever there is a formation of carbocation, whenever a complete carbocation is formed, C positive, it always try to undergo rearrangement to give a more stable carbocation, and nucleophile attacks on the most stable carbocation to give the most stable product, right? Let's move ahead. Student, I was having my alkyl halide, right? First the reaction is initiated by a solvent, so I will have in the first transition state this R and X. I will have ionization, R will have delta positive, and basically this will get ionized by solvent. Let us assume I am having water as a solvent, H plus, OH, right? Del positive. So can I say this H del positive and X del negative, they will try to form bond. So I will have a tendency, this X will have a tendency to get depart, right? Now, so in the transition state, basically X is departing. It has not still departed, it's trying to depart. Now what will happen? Finally it will depart, and I will have the formation of my first intermediate, carbocation. This carbocation is obtained as intermediate. Once this intermediate is obtained, it may undergo rearrangement to give a more stable carbocation, and on the final intermediate, the nucleophile will approach. So in that transition state 2, I will have nucleophile approaching, right? And finally I will have the formation of my product, right? So here the nucleophile is substituting the halide ion, right? How many products? 2 products. They will be mirror image of each other. If chirality is there, we may get racemic mixture also, right? I hope you understood this Sn1 mechanism. I am having an alkyl halide once again. The reaction is initiated with the help of a solvent, so solubilisis, ionization, formation of a carbocation. The nucleophile is approaching from the front as well as from back because the molecule is planar. On a planar molecule, the nucleophile can approach from the front side as well as from the back side. So two products, right? Now, one more thing. No doubt the racemization will be there. But will we have 100% racemization? No. In general, student, we will get two product, one inverted product, one retented product. What do we mean by inverted product? Nucleophile has attacked from back side, inverted. Nucleophile has attacked from the front side, retented. The extent of inversion will be more. Why? Because you can understand it like this. As this leaving group is departing and the nucleophile is also approaching from the front side, can I say it will experience inter-electronic repulsion, inter-anionic repulsion? If the nucleophile approaches from the back side, it won't experience any steric crowding, it won't experience any hindrance. So inverted product will be somewhat more as compared to retented product, right? So 100% racemization does not occur. I hope you understood this one also. Let's move ahead. What are the factors which affect SN1 reaction? Okay, students, in SN1 reaction, in the first step, I will have the formation of this carbocation. This is my rate determining step. And in the second step, the nucleophile is approaching. First step, we'll write rate law expression on the basis of rate determining step. What species are involved in this rate determining step? Substrate itself. So can I say rate of reaction is directly proportional to substrate concentration? Can I say this SN1 reaction is independent of nucleophile? Because the nucleophile is attacking in the second step, which is relatively a faster step, right? Since the nucleophile is attacking in second step, SN1 reaction generally does not depend on the nature and the concentration of nucleophile. Students, always remember a weak or a moderate type of nucleophile, moderate type of nucleophile will promote SN1 reaction. Now, this one. Will the rate of reaction also depend on the concentration of substrate? Yes, this rate of reaction is directly proportional to the concentration of substrate. What's the order? What is the power here? 1. So SN1 is a first order reaction. What is the molecularity? How many molecules are involved in this rate law expression? Only one. Unimolecular reaction, right? Okay. Now, can I say in the first step, which is the ionization step, there is a formation of carbocation. More is the stability of carbocation, higher will be the rate of reaction, right? Or more is the stability of carbocation, better will be the tendency of this leaving group to get depart. It will ionize or it will get departed only when this R plus and Lg minus is stable. So rate of reaction will also depend on the stability of carbocation. Now, can you tell me which carbocation is more stable? A 3-degree carbocation or a resonance stabilized carbocation? So can I say 3-degree carbocation or resonance stabilized carbocation? Resonance stabilized carbocation will promote SN1 reaction, and the rate will go like this: 3-degree max, then we will have 2-degree. SN1 reaction will not occur in 1-degree generally, or in case of methyl halides or halomethane. Why? because obviously the carbocation will be methyl carbocation, which is a highly unstable carbocation. Right, students? Okay. Will the rate of reaction also depend on the leaving ability of the leaving group? Yes. In the first step itself, there is a ionization. The first step itself is the ionization, which is nothing but the rate determining step. Better is the leaving ability of the leaving group, faster the rate of reaction, right? So Sn1 reaction will also depend the leaving ability of the leaving group. Let's write here. Sn1 will also depend on leaving ability of Lg. Lg stands for leaving group, right? Now let's suppose I am having alkyl halides, Rx, that is Rx. I am having Ri, Rbr, Rcl, Rf. What do we say? If the nature of alkyl is same, if the same alkyl group is there, where I will have a faster Sn1. In case of alkyl iodide, Ri better, then we will have Rbr, Rcl, and in Rf it will be at a very slow rate because fluorine is a poor leaving group. I hope you understood Sn1. Let's summarize it. Two-step process. First step, ionization. Second step, attack of nucleophile. Second, we will have racemization, but will we have 100% racemization? No. Formation of carbocation. The carbocation formed may undergo rearrangement. On the most stable carbocation, the nucleophile will approach from the front as well as from the back. If I talk about the rate law expression, rate of reaction directly proportional to substrate, independent of nature of nucleophile as well as the concentration of nucleophile. Poor to moderate type of nucleophile promotes Sn1 reaction. Generally neutral nucleophile like water, alcohol, H2S, such type of species will promote Sn1 reaction. Right? I hope you understood Sn1 reaction. Let's move ahead. Now, the second type of pathway in nucleophilic substitution reaction, and that is Sn2 pathway. Student, in the beginning only I told you, there is a feasibility that the nucleophile and the leaving group, attack of nucleophile and the departure of leaving group is occurring at the same time. Then can I say the reaction will get converted to a single step? In the previous step, first the leaving group was departing and then the nucleophile was attacking. Here, the attack and departure. As it is approaching, this one is departing. As it is approaching, the second one is departing, right? So the attack of nucleophile and the departure of leaving group is occurring at the same time. So it is going to be a one-step process. Here we will not have intermediate, we will have only transition state. Let's see. A nucleophile is coming, it's approaching from the back side. As soon as the nucleophile is approaching this carbon, halogen is getting departed in the form of halide ion. First, I will have transition state. If I look at this transition state, how many species are connected? 5. So can I say penta-coordinated? Penta-coordinated. Let us talk about the hybridization. sp2, so planar, right? Someone may say, sir, why not sp3d? Student, these bonds are partial bonds. One is trying to get connected, one is trying to get departed. Okay, one more thing. If I talk about this transition state, can I say it is having a dianionic character? Dianionic character. We'll write each and everything. Okay, if it is having a dianionic character, can I say electron withdrawing group will promote Sn2 reaction, right? Anion gets stabilized by a electron withdrawing group. Next, what will happen? The nucleophile will attack from the backside. This bond will get connected. This one has to get departed, right? So can I say, Since the nucleophile is approaching from the backside, we'll get only one product, and that is the inverted product. Inverted product. Right, student? We say this phenomenon as Walden inversion. Only inverted product is visible here. Let us move ahead. See, I'm having an alkyl halide. The nucleophile is approaching in the transition. This is the transition state, right? Okay. And finally, the nucleophile has attacked to this carbon from the backside. It's bonded to the carbon from the backside. I'll get the inverted product. I hope you understood this one. Now, one more thing. Can I say this is the energy of reactant and this is the energy of transition state? This is nothing but the activation energy barrier. More is the stability of transition state, higher is the stability of transition state, higher is the rate of reaction, right? The activation, more is the stability, lesser will be the energy, lesser will be the activation energy gap, faster will be the rate of reaction, right? And can I say this transition state will get stabilized by electron withdrawing group or resonance, right? So if the alkyl group connected here is having a vacant p orbital, then resonance will occur, and in that particular case transition state will be more stable, the rate of Sn2 will be faster. Let's move ahead. Stereochemistry of Sn2 reaction. In Sn1 reaction I was having racemization, two products, not 100%, inverted was more, retented was less. In Sn2 reaction I'm having 100% inversion only. The nucleophile is approaching from the backside, right? Okay, so we will have complete inversion, and this inverted product is, we say this phenomenon as Walden inversion, right? So suppose if I'm having a substrate like this, you can see here itself, leaving group and the nucleophile. Leaving group was on this side, the nucleophile has attacked the carbon from the back side and it's bonded to the back side. So 100% inversion only. If leaving group is on the wedge, then the nucleophile will get attached on dash. I hope you understood it. Let's move ahead. What are the factors which affects Sn2 reaction? Sn2 reaction, single step reaction. Single step reaction, right? If it's a single step reaction, in the first step itself, the nucleophile as well as the substrate both are involved. So can I say the rate of reaction is directly proportional to RLG? It's also dependent on the concentration of nucleophile as well as on the nature of nucleophile. A stronger nucleophile will promote Sn2 reaction. Stronger nucleophile will promote Sn2 reaction. For Sn1 reaction, we need moderate or weak type of nucleophile. For Sn2, the rate of reaction is involving nucleophile also. So a stronger nucleophile will promote Sn2 reaction. Students, now let us focus on the substrate part. How the rate of reaction will be dependent on substrate also. This one. Okay. Students, in Sn2 reaction, the role of nucleophile is involved, and nucleophile prefers to attack on less sterically crowded carbon, right? Now, if I am having 1 degree alkyl halide, 2 degree alkyl halide, 3 degree alkyl halide, what do you say? In which case we are having more steric crowding, 3 degree alkyl halide. So, will the nucleophile prefer to attack on 3 degree? The answer is no. So, the rate of Sn2 reaction faster in rate of Sn2 more in case of 1 degree or methyl halide. Then we will have 1 degree alkyl halide, 1 degree alkyl halide, then 2 degree then 3 degree. In 3 degree alkyl halide, 3 degree alkyl halide, Sn2 will not occur. I hope you understood this one also. So there, if I talk about substrate, methyl, then 1 degree, and then maximum up to 2 degree. In 3 degree, there is no Sn2, right? Okay. If I talk about nucleophile, stronger nucleophile will promote Sn2 reaction. All the anionic nucleophiles and nitrogenous nucleophiles are stronger nucleophile. They will promote Sn2 reaction, right, student? Let's move ahead. Now let's compare when we will have Sn1 and when we will have Sn2. Most of the time I find student faces difficulty in order to understand whether the reaction will occur via Sn1 pathway or Sn2 pathway. We'll summarize whether the reaction will occur via Sn1 or will occur via Sn2. Let's see. If I talk about the energetics, Sn2 single step process, I am having only transition state. Here 2 transition state accompanied by 1 intermediate, at least a minimum of 1 intermediate. Even we can have more than 1 intermediate if the carbocation is undergoing further rearrangement, right? Okay. If I talk about kinetics, of Sn2, the rate of reaction depends on substrate as well as nucleophile. Substrate, nucleophile. Here the rate of reaction is simply dependent on substrate in Sn1. So unimolecular, bimolecular. If I talk about stereochemistry, in Sn2 we will have complete inversion. Here we'll have racemization, right? Rearrangement. Is any intermediate formed here? Is any intermediate formed in case of Sn2? No. Is there any carbocation formed in Sn2? No. So there is no rearrangement possible. Here, since the carbocation is formed, and if the carbocation formed is less stable, and if it is having an option to undergo rearrangement, definitely it will undergo rearrangement, right? Next, activation energy. Obviously, activation energy of Sn2 will be faster as compared to Sn1, right? Sn2 is all about speed. It's basically governed by nucleophile. Sn1 has nothing to do with nucleophile, right? Okay. Nature of substrate. If I talk about Sn1 reaction, 1 degree, 2 degree, in 3 degree, Sn2 reaction will not occur. If I talk about Sn1 reaction, 3 degree, here the rate of reaction will depend on the stability of carbocation. More is the stability of carbocation, faster the rate of reaction, right? If I talk about nucleophile, all the strong anionic nucleophile will promote Sn2 reaction. Weak or moderate type of nucleophile or the neutral nucleophile will promote Sn1 reaction. Neutral, moderate, Sn1, strong anionic nucleophile, Sn2. Living ability. Here also, the rate of Sn2 will also depend on the living ability of the living group, because in the first step, only the living group is getting departed, right? And the rate of Sn1 will also depend on the living ability of living group. If I talk about solvent, Sn2 reaction generally is not promoted by a solvent. So even a polar aprotic solvent will promote Sn2 reaction. Why polar protic solvent will not promote Sn2? The reason is, if I am having a polar protic solvent and if the nucleophile is strong, the nucleophile itself will react with the solvent, right? That's why polar aprotic solvent generally favors Sn2 reaction. Like I am having DMSO, ether, all these things, solvents will promote Sn2 reaction. If I am having a polar protic solvent, then a polar protic solvent will promote Sn1 reaction, right, student? Temperature. For Sn2 reaction, the temperature is relatively high, it's relatively less in case of Sn1 reaction. I hope you understood the basic difference between Sn1 and Sn2. Please go through this table once again. Now let's move to the next type of substitution reaction, that is Sni reaction. Students, this particular reaction mechanism is very important, but I have seen in the comment section most of this class 11 students are also watching this lecture. So we are going to discuss the mechanism once we have covered hydrocarbon. Then you will have a clear-cut understanding of reaction mechanism. In alkyl halide chapter, we will discuss the mechanism of this pathway. How does Sni reaction occurs? If I'll talk in lecture 3rd itself about the pathway of this reaction, it will be very tough for lot of class 11 students to understand it. Okay, so let's simply write the reaction. The best example of Sni reaction is this reaction. I'm having an alcohol ROH. It is treated with a solvent SOCl2. Right? Here what happens? This is a chlorinating reagent. And what this chlorinating reagent will do? It will do the substitution. Simply the alcohol will get substituted by chlorine and I will have the formation of alkyl halide. Now here, if I talk about the stereo, it's all about retention. If I talk about the stereochemistry of Sni reaction, here retention of configuration occur. Let's try to understand it. I'm having a substrate like this. Alcohol is there on the wedge. And now if it is treated with SOCl2, what will happen? Can you tell me? Simply, this alcohol will get substituted by chlorine and chlorine will be there on the wedge. I hope you understood this one. Intramolecular Sn pathway. We'll discuss the mechanism in the chapter alkyl and aryl halides, which is after hydrocarbon. So the next lecture is going to be on hydrocarbon. Then we'll discuss alkyl and aryl halide. And students, basically whatever we are discussing, we'll do the applications of all these reactions. We'll do at least 20 to 30 questions on each pathway in the chapter alkyl and aryl halides. That particular chapter will do most of the time we'll be practicing question itself. That's why I'm trying to complete the theoretical part in this lecture so that we can understand the next chapter, hydrocarbon. Let's move ahead. Next one, SNNGP. Nucleophilic substitution reaction by neighboring group participation. In this particular reactions, we are having one internal nucleophile, as well as external nucleophile. Two nucleophiles are there. Nucleophile. The position of internal nucleophile, it should be from 3rd carbon onwards. Right? Position of internal nucleophile. I will try to explain, don't worry. Nucleophile, it should be from 3rd carbon onwards with respect to the leaving group. Let us suppose I am having species like this, Lg. So the nucleophile should be present from 3rd carbon onwards. Either it can be on the 3rd carbon, it can be on the 4th carbon, can be on the 5th, means from 3rd carbon onwards. This nucleophile has to be present. Now, we should have one external nucleophile also. Now, first one, which reaction will occur? Intramolecular reaction. So, this internal nucleophile will attack here. Right, student? First, the internal nucleophile will attack here. As soon as it attacks here, the leaving group will depart. And I will have a cyclization. It supports 3-member cyclization, 4-member cyclization, 5-member cyclization onwards. Lesser the cyclic ring, if I am having a 3-member cyclization, faster will be the reaction, right? So 3-member cyclization faster, then 4, then 5, and then 6. Okay. Now, once the cyclic part is formed, let us assume I am having C, 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 and this is connected to NU like this, right, student? Now the role of this external nucleophile will come. Now this external nucleophile may approach here also, and it may approach here also. As soon as it approaches on either of the carbon, one of the bond will break, right? So two times attack is occurring. In the first step, we'll have the back attack. Once again, the external nucleophile will also do the back attack itself. Two times inversion. So final product will be retented one only. I will have retention of configuration. So if I summarize this SN-NGP, first, two nucleophiles are important, internal as well as external nucleophile. The reaction is initiated by a internal nucleophile. First, internal nucleophile attacks from the backside. I will have a cyclic ring, right? Once the cyclization is there, now the external nucleophile approaches. It may approach on both the carbons, so I will have two different products, right? If I talk about the stereochemistry, first step I was having inversion, second step also I'm having inversion. Inversion is nothing but double inversion is nothing but retention. So this is all about SN-NGP. Student, this particular reaction is really important, and I promise you we'll do minimum of 15 questions from this particular subtopic. In alkyl aryl halides, in alcohol phenol etho, everywhere we are going to discuss a lot of questions on this particular concept. So you don't need to bother. Let's move ahead. Student, now let's talk one of the most important reaction. It's basically nothing but SN1 reaction and SN2 reaction only, but we'll say it as Sn prime, Sn1 prime and Sn2 prime. When does this reaction occur? Let us try to understand. Student, if I'm having a substrate like this, R, CH, doubly bonded CH, singly bonded CH2X. Or if I'm having a substrate like this, CH2X. Can I say both of them are 1 degree alkyl halide? 1 degree alkyl halide, right? And if they are 1 degree alkyl halide, they will promote Sn2 reaction, right? Okay. So will Sn2 reaction occur here? Definitely yes. This halogen is connected to a 1 degree carbon, 1 degree alkyl halide. This carbon is a 1 degree? Because this particular carbon is connected to one carbon in the chain, right? 1 degree alkyl halide, it may undergo via Sn2 pathway. If I look at this particular substrate, once again halogen is connected to 1 degree alkyl halide only. So here also we'll have Sn2 reaction. Will Sn1 reaction occur in both the cases? The answer is still yes. Even Sn1 reaction will also occur. How? Because as soon as the ionization occurs, we'll have a resonance stabilized carbocation. Let's see. I'm having R, CH, doubly bonded CH, single bond CH2 positive. Is it resonance stabilized? The answer is yes. Is it also resonance stabilized? The answer is still yes. CH2 positive. This one is also resonance stabilized. Second one is also resonance stabilized. So it will undergo Sn1 as well as Sn2. Right? Now, if I am given a substrate like this, RCH, CH, CH2X, and now you are given a nucleophile, will you say, so which type of reaction it will undergo? Now, here the reaction pathway will be dependent on nature of nucleophile. If the nucleophile is strong, if Nu minus is strong, then the reaction will occur via Sn2 pathway. The reaction will simply occur via Sn2 pathway, right? Okay. If the nucleophile is weak, if Nu minus is weak, then reaction will occur via Sn1 pathway, right? So in case of such compounds are referred as allylic system. This carbon is referred as allylic carbon. Allylic carbon, right? This carbon is referred as benzylic carbon. So in case of allylic halides, in case of benzylic halide, how it is a benzylic halide? This carbon is directly connected to a benzene ring. Carbon connected directly to a benzene ring is referred as benzylic carbon. In case of allylic halides, in case of benzylic halides, we'll have both Sn1 and Sn2. Now the reaction pathway will simply depend on nucleophile and solvent. If it is a strong nucleophile, polar aprotic solvent, the reaction will occur via Sn2 pathway. If it is a moderate or weaker nucleophile and the solvent is polar protic, the reaction will occur via Sn1 pathway. I hope you understood it. Let's move ahead. Students, now it's time to discuss elimination reaction. You may say, sir, we have not done even a single question. I totally agree, we could not do questions related to nucleophilic substitution reaction. But student, it's my promise, we'll do sufficient number of questions or enough questions on this nucleophilic substitution reaction in the chapter alkyl and aryl halide. That particular chapter is all about the applications of these reactions itself. First, we are discussing the theory part here. Lecture number 5 will do the problems related to these theoretical aspects. Okay, so now let's focus on elimination pathway. Elimination. Okay, basically students, here 2 sigma bonds are removed and we'll have the formation of 1 pi bond. Removal of 2, departure of 2 groups, one Y, one Z, and I will have a formation of pi bond. 2 sigma bonds broken, 1 pi bond formed. Can you comment on the energetics of this process? Yes, this process is endothermic, right? Endothermic reactions. And endothermic reactions are supported at high temperature. So elimination is favored at high temperature. Substitution relatively lower, elimination at higher temperature, right? Okay. Now we will have different types of elimination. The first one, alpha elimination. Second one, beta elimination, and the third one, gamma elimination. Student, we'll discuss one by one, but most of the cases will be, or most of the time we'll be talking about beta elimination, because in the next upcoming chapters, hydrocarbon, alkyl aryl halides, alcohol phenol ethers, will be talking a lot, or will be doing a lot of applications of these beta eliminations. This beta elimination is really important for us. But first of all, let's talk briefly about this alpha elimination. Students, let's talk about this alpha elimination. If I focus here, can I say, basically with the help of a base, I am removing 2 groups from the same carbon. When 2 groups are removed from the same carbon with a base, such an elimination is referred as alpha elimination. I will take one example. I am having CH, Cl, L and L. Carbon containing leaving group, carbon containing halogen is referred as alpha carbon. Now on this alpha carbon itself, hydrogen is also present, right? Okay. Now this particular compound is treated with a base. Let us suppose OH minus. What is the function of base? To snatch acidic hydrogen. So this base OH minus will snatch this hydrogen. I will have the formation of C negative, Cl, Cl and Cl. 3 leaving groups. What happens? One of the leaving group will get departed. So here H is getting departed, Cl is getting departed. I will have the formation of HCl. One H and one Cl is removed from the same carbon, right? That's why it's a alpha elimination. And what I will have? I will have the formation of C, Cl, Cl and one unshared pair of electron. So alpha elimination of this chloroform, this particular species is chloroform. Alpha elimination of chloroform will lead to the formation of carbene. And this particular substrate is called dichlorocarbene. Dichlorocarbene. I hope you understood this one also. Let us move ahead. Beta elimination. Student, this particular elimination is really important for us. When the two groups are lost from adjacent atom and we will have the formation of a pi bond, then the elimination is referred as beta elimination. Let's try to understand it. I'm having hydrogen here and halogen here. Okay. Now, carbon containing halogen, carbon containing leaving group is referred as alpha carbon. So can I say this carbon is beta carbon? Now I will have a base B minus. What is the function of base? To snatch acidic hydrogen. What this will do? It will snatch one hydrogen from beta carbon. So for beta elimination, presence of beta hydrogen is mandatory. If there is no beta hydrogen, this elimination will not occur. Now, what will happen? As soon as this base snatch this H in the form of H plus, I will have carbene. I will have carbon ion. This carbon ion will delocalize and this one will get departed. So what I will have? I will have the removal of H from beta carbon, X from alpha carbon. Finally, I will have the formation of alkene, C double bond C. From beta carbon, I am removing hydrogen. From alpha carbon, I am removing the leaving group, namely halogen. Right? Such an elimination is referred as beta elimination. We are going to discuss a detailed about this beta eliminations. We are having different pathway. It's feasible. The base or the attack of base on this acidic hydrogen and the departure of leaving group occur at the same time. It is also feasible first the leaving group departs and then the base attacks. It is also feasible first the base snatches this hydrogen. I will have the formation of carbon ion and then the departure of leaving group. So there are different pathway through which this beta elimination may occur. We'll discuss a lot about that. You don't need to bother. Gamma elimination. What will happen here? I'm having one leaving group here and one leaving group or hydrogen here. The base will snatch acidic hydrogen from here, right? I will have the formation of nucleophile and then this nucleophile will do the internal attack and I will have cyclization. But this is not that important. For us, the most important is beta elimination. Student, now it's time to talk about beta elimination. First one, we are having different pathway through which this beta elimination may occur. The first pathway is E1 pathway. E1. We have studied Sn1. What was happening in Sn1? Ionization of the leaving group, right? Same story here. First, the leaving group will depart. I will have the formation of carbocation and in the second step, the base will snatch the acidic hydrogen. First step, slow step, involves the ionization to form carbocation. I can have, right, halogen. The first step, ionization, departure of leaving group, formation of carbocation. Now in the second step, a base B minus will approach and will snatch the beta hydrogen from here and I will have the formation of alkene, right? I hope you understood this one. If I talk about the mechanism, student, once again, the first step is initiated by a solvent. The solvent does the ionization process. I will have the formation of carbocation. The carbocation once formed may undergo rearrangement. to give us more stable carbocation. Once the most stable carbocation is formed, then we remove beta hydrogen with respect to this carbocation. We remove hydrogen from the neighboring carbon to form alkene. So first I will have the formation of carbocation. In the second step, what is the base doing? It is snatching beta hydrogen. You can say this carbon is alpha carbon. This particular carbon is going to be the beta carbon. I am removing hydrogen from beta carbon, right? As soon as this hydrogen is removed, I will have the formation of alkene. Just like Sn1 pathway, the first step is the RDS, rate determining step. Whenever a carbocation is formed, the formation of carbocation always occurs at a slower rate. I hope you understood this one. What are the factors which affects the rate of E1 reaction? Here, if I will write the rate law expression, can I say we write rate law expression for RDS itself, and in RDS is the base involved? No. Attack of base occurs in the second step, which is a fast step. So in RDS only substrate is involved. Rate of reaction is directly proportional to Rx. Can I say in the first step we will have a formation of carbocation? More is the stability of carbocation, higher is the rate of E1 reaction. So rate of E1 reaction, can I say rate of E1 3 degree max, then we will have 2 degree. In 1 degree this E1 will not occur, or will occur at a very extreme condition, right? Okay, rate of E1 reaction. Will it depend on the nature of base? Not at all. The attack of base is there in the second step, independent of base. It does not depend on the concentration as well as the nature of base. So even a weak or moderate type of base, even a neutral nucleophile like H2O, if I will support heat, if I will provide higher temperature, elimination reaction will occur. Let's write that moderate or poor base will promote E1 pathway. I hope you understood this one. Let us move ahead. Now student, let's talk about E2 pathway. Once again, it's an application of beta elimination. Here what will happen? I'm having CX hydrogen. Now here basically what happens, the attack of base on this hydrogen and the departure of leaving group occurs simultaneously. The attack of base on acidic hydrogen, that is beta hydrogen, and the departure of leaving group occurs at the same rate. So it will occur simultaneously. So can I say E2 will be a one-step process, right? Okay. The best example is dehydrohalogenation. What do we mean by dehydrohalogenation? D means removal, hydro, hydrogen, halogenation, halogen. So removal of one hydrogen and one halogen, right? We remove hydrogen from the beta carbon and halogen from alpha carbon. Dehydrohalogenation is the elimination of hydrogen and halogen from an alkyl halide to form alkene. It can occur via E1 pathway, just now we had done. Even it can occur via E2 pathway. If I talk about E2 pathway, student, it's a one-step process, okay? And if it is a one-step process, can I say the rate of reaction will be dependent on both substrate as well as base? So can I say here a strong base will promote E2 reaction. A strong base will promote E2 reaction. How? And what are the different types of strong base? The best one is alcoholic KOH. We can have NaNH2. These are some of the bases which will promote E2 reaction. Alcoholic KOH always favors E2 pathway if the substrate is 3 degree. Let's talk about the mechanism of this reaction. The base is attacking on beta hydrogen. The attack of base and the departure of leaving group is occurring at same time. Now I'm having a transition state like this. This is my TS. We don't have any intermediate. There is no formation of carbocation, so there is no rearrangement in E2 pathway. This point is very important. In E2 we don't do rearrangement. Whenever you have alcoholic KOH and 3 degree alkyl halide, don't do rearrangement. Directly form the alkene through TS. Okay, now can I say this TS is having a nature of partial double bond? So basically it's sort of alkene type, and alkene depends on, or the stability of alkene depends on hyperconjugation, right? More is the number of alpha hydrogen, more is the alkyl group substituted here, more will be the stability of TS, and more is the stability of TS, lesser will be the activation energy barrier, higher will be the rate of reaction, right student? So TS is having partial double bond character, double bond character, right? So can I say TS will be more stable if I am having more number of alpha hydrogen, and if I am having more number of alpha hydrogen, TS is more stable, rate of reaction will be faster. So once again, can I say here also the rate of reaction will be more in 3 degree than 2 degree. In 1 degree alkyl halide, this E2 will not occur under normal condition. It will occur faster, at a faster rate in case of 3 degree alkyl halide. Why? Because in 3 degree alkyl halide we will have more hyperconjugation, right students? Because TS is having a alkene type of character. Okay. So students, now let's discuss a very important scenario. Okay. Just focus on this particular substrate. Can you see this carbon as the alpha carbon? Alpha carbon. Now, can I say then this carbon as the beta carbon? Can I say this carbon also as the beta carbon? Right student? This is my beta carbon. Can I say this one also as beta carbon? Right? This one also as the beta carbon. How many beta carbons I am having? 3 different beta carbons, right? One, this one, methyl group, methyl group. These 2 beta carbons are same, simply a methyl group. If I talk about this particular carbon, this one, can I say it's a 2 degree carbon, right? How it is a 2 degree carbon? Because on the left side also it is connected to 1 carbon, on right side also it is connected to 1 carbon. This carbon is a 2 degree carbon. This particular carbon is going to be a 1 degree carbon or even 1 degree carbon. These 2 beta carbons are same, so the beta hydrogen nature will also be same. Now, when we are having 2 different types of beta hydrogen, the question is which one we will remove. The base will attack on which beta hydrogen. Student, let's see. Let us assume the hydrogen connected to a 2 degree beta hydrogen is HA. This one is HA, and the hydrogen connected to 1 degree beta carbon is HB. If the base is attacking on HB, then I will have the formation of, I will simply remove this hydrogen and this one, so I will have simply the formation of CH2 double bond CH3 CH2 CH3, right? So if I am removing hydrogen, or if I am removing beta hydrogen from 1 degree carbon here, I am getting this alkene. It's simply formed by the removal of this beta hydrogen. Okay, if I am removing beta hydrogen from a 2 degree carbon from here, I am getting this product. Now, which one is more stable product? Which one is more stable product? Student, if I talk about this alkene, here I'm having how many alpha hydrogen? 3 from here, 3 from here, 3 from here. 9 alpha hydrogen. Here, if I talk about this particular compound, I'm having 2 alpha from here and 3 alpha from here. So total of 5 alpha hydrogen. Which one is having more number of alpha hydrogen? First one, right? This one is having 5 alpha hydrogen. Now, stability of alkene simply depends on the number of alpha hydrogen. More is the number of alpha hydrogen, higher is the stability of alkene. So, students, in beta elimination, if you remove hydrogen from more substituted carbon, basically you are going to get a relatively more stable alkene, and that alkene is referred as ZF alkene, more alkylated alkene, more number of alpha hydrogen. If you remove beta hydrogen from less substituted carbon, in that case you are going to get Hofmann alkene, less alkylated alkene. Simple. If I am having two different types of beta hydrogen, if you are removing beta hydrogen from the more substituted carbon, in that particular case, most you will get ZF alkene, relatively more stable alkene. If you are removing beta hydrogen from a less substituted carbon, you are going to get Hofmann alkene, less stable alkene. I hope you understood what do we mean by the term ZF alkene, Hofmann alkene. ZF, more number of alpha hydrogens. Hofmann, less number of alpha hydrogen, less stability, right? Let's move ahead. Now the question is, when do you form ZF alkene and when do you form Hofmann alkene? In most of the cases, if you are having a base like alcoholic KOH, NaNH2, in such cases, or mainly alcoholic KOH, in that case RO minus, in all such cases you will form ZF alkene if the leaving ability of the leaving group is also good. If the leaving groups are iodide and all other leaving groups like tosylates and all these things, in that case you are simply going to form ZF alkene, more substituted alkene. Now we need to discuss the case where we are going to form Hofmann alkene. Let's discuss about that also. Formation of Hofmann product. Student, if base is very bulky, can you name one bulky base? The best answer is terbutoxide ion. If I am having a highly bulky base, or if I am having a poor leaving group like fluoride ions, in all such cases, you are going to form less substituted alkene, or if there is steric crowding at gamma carbon, in that case also you are going to form Hofmann alkene. I have told you three cases. First, the base is very bulky, means the base is terbutoxide ion. In that case, base, if the base is like this, it will always promote Hofmann elimination. Okay, Hofmann elimination. Second, leaving group is poor. Leaving group is poor. Mainly fluoride ions, Nr3 positive, like this. In such cases, you are going to form Hofmann alkene. Third, one more case. If there is steric crowding at gamma carbon, carbon containing halogen alpha, the neighboring one is beta, and the neighboring of beta is gamma. So if there is 3 degree or more substitution at gamma carbon, if there is lot of steric crowding at gamma carbon, in that case also you are going to form Hofmann alkene. Let's read it. Bulky bases can accomplish dehydrohalogenations that do not follow ZF rule. Due to steric hindrance, a bulky base abstracts a less hindered proton. Often that one leads to the formation of least substituted product called Hofmann alkene. Mainly because of, in a simpler word, if I simply summarize it, more is the steric crowding on base. Obviously it will snatch, or it will prefer to snatch that hydrogen which is less crowded, right? Because the base is already sterically hindered. So in that case, we are going to get Hofmann alkene. Let's move ahead. Student, now the stereochemistry of E2 reaction is very important. Stereo of E1 is not quite clear, right? Simple planar geometry, the base will simply come and will attack. So it's not that important. But stereochemistry of E2 reaction is highly important. For E2 reaction to occur, I will simply say in a simple word through example. For if E2 reaction has to occur, the beta hydrogen and the leaving group should be anti-periplanar. The beta hydrogen and the leaving group. If this leaving group is on the wedge, the beta hydrogen has to be there on the dash. If anti-periplanarity condition is not satisfied, student, in that case you are not going to do E2 reaction. Simply you are not going to do E2 reaction if anti-periplanarity condition is not fulfilled. Now what do we mean by the term anti-periplanarity? First, this hydrogen and halogen has to be there in the same plane, then only I will have the formation of alkene, right? So periplanarity, now anti, both hydrogen and halogen has to be at anti position with respect to each other, then only I will have the formation of, or I will do E2 pathway. Let's try to understand. I'm having halogen here, two alkyl groups. Now here, student, this one alkyl hydrogen is here, and here I'm having, now on the dash I'm having alkyl group. Okay, and now it is treated with a strong base ETO minus, RO minus. Tell me, will elimination occur? Will elimination reaction occur here? The answer is no. Why? No doubt halogen is there. This is also the beta carbon. At this beta carbon we don't have any hydrogen, so elimination won't occur from this side. Now here I am having beta hydrogen, but the beta hydrogen and halogen, they are on the same side. Beta hydrogen, H and X, they are on the same side. Anti-periplanarity condition is not fulfilled, so E2 will not occur. For E2 to occur, beta hydrogen and halogen has to be anti with respect to each other. If one is at wedge, other has to be at the dash. I hope you understood this one. Let's move ahead. Let's do the comparison of E1 and E2 reaction. E1, simply weak base will promote E1 reaction because the first step is ionization carried by a solvent, solvolysis. So here the role of base is there in the second step, which is a fast step. E1 is simply supported by a weak to moderate type of base. In E2 single step reaction, strong base favors E2 reaction, mainly alcoholic KOH and NH2, right? Second one, solvent. Obviously E1 reaction is initiated by a solvent, so polar protic solvent will favor E1 reaction. Here we can have any solvent, and generally aprotic solvent. In general, not always, in general aprotic solvent will favor E2 pathway. Third one, if I talk about the substrate, 3 degree, 2 degree, here also 3 degree, 2 degree. 1 degree, in 1 degree we won't have E1. Why? Because 1 degree carbocation is highly unstable. Next, students, if I talk about the leaving ability in both the cases, in E1 as well as E2 reactions, the leaving ability of the leaving group is important. So in both the case, good leaving group will promote E1 as well as E2. Next, talk about the kinetics. Obviously in E1 reaction, the first step is the rate determining step, and in the first step only substrate is involved, so it's a unimolecular reaction independent of base, so it's a first order reaction. If I talk about E2, it's a one step process. In the first step itself, the base as well as alkyl halide both are involved, so second order reaction. First order with respect to alkyl halide and first order with respect to base. I hope you understood this one also. Orientation. Both E1 and E2 will promote or will favor the formation of more stable product, that is more stable alkene. So both E1 as well as E2 will promote ZF alkene. Next one. If I talk about stereochemistry, in E1 no such requirement is there, but in E2 reaction anti-periplenarity is must. I hope you understood this one. Let's move ahead. Now students, it's time to talk about the third type of beta elimination, that is unimolecular elimination, conjugate base elimination process. In case of beta elimination, I'm having this carbon and here I'm having one hydrogen, right? We remove hydrogen from beta carbon and from alpha carbon we remove this halogen. Now we have discussed the first case where first in E1 reaction the departure of leaving group was occurring first and then the beta hydrogen was snatched. In the second case, the departure of beta hydrogen and the departure of halogen was occurring at the same rate. Now we may have also one possibility that first this beta hydrogen is snatched by a base, will have the formation of a carbon ion. This carbon ion is nothing but a conjugate base, and then it will delocalize and the leaving group will get departed. So such reactions are referred as E1CB reactions. Here I will have the formation of carbon ion. Now when we will have E1CB, let's see the case. In this reaction, hydrogen leaves first and then halogen. This is a two-step process. First, I will have the formation of carbon ion, and in the second step, the departure of leaving group. Okay. The removal of proton by a base generating a carbon ion in the first step. Base, it simply snatches one beta hydrogen. I will have the formation of carbon ion. This carbon ion is nothing but the conjugate base. In the second step, this carbon ion delocalizes and the departure of leaving group occurs to form alkene. The reaction is occurring in two different steps. You can say, sir, which one is the slower step? Simple. I'm having first step, formation of carbon ion. Second step, departure of leaving group. Student, E1CB reaction is only promoted when the leaving group is very poor leaving group. And if it is a poor leaving group, can I say the departure or the leaving ability of such leaving groups will be very less. So departure of leaving group will occur at a very slow rate. No doubt here also I'm having the formation of carbon ion. This one is also a slower step. But the second step is even more slower, and because of that, second step is going to be the rate determining step in E1CB reaction. Let's move ahead. The strong base abstract beta hydrogen in the fast reversible step. As a result, carbon ion intermediate is formed. Now in the second step, which is relatively even more slower, the departure of leaving group occurs. Right? If I talk about the molecularity, unimolecular first order reaction. Right? It's a unimolecular first order with respect to carbanion. If I talk about the overall order, then it's a second order reaction, student. This one is very important. It's first order with respect to carbanion. If I talk about the overall order, then the order is 2. Let's move ahead. Now the question is, when does this E1CB reaction will occur? Two conditions. If the leaving group is very poor, E1CB, or if the beta hydrogen is highly acidic. If the beta hydrogen is highly acidic, then in that case also E1CB reaction will occur. So two cases, leaving group, poor, and beta hydrogen highly acidic, right? I hope you understood it. So if I'm having a beta elimination, if the beta hydrogen is acidic due to the presence of electron withdrawing group at beta carbon, in that case I will have reaction occurring via E1CB pathway. And here in E1CB reaction, most of the cases will form less substituted alkene, that is Hofmann alkene. Okay. So when the leaving group is strongly electronegative, when the leaving group is relatively poor, these are the highly electronegative leaving group. Because of that, the acidic strength of beta hydrogen increases, and if the acidic strength of beta hydrogen is more, I will have the formation of carbon ion. Reaction will occur via E1CB pathway. Presence of electron withdrawing group, already I have told you. Because of that, the acidic strength will increase. Poor leaving group favors E1CB reaction. I hope you understood this one. Let us move ahead. Let's take one example of E1CB reaction. I'm having a quaternary ammonium salt. What do we mean by quaternary ammonium salt? Nitrogen connected by 4 alkyl groups. So it will have a positive charge and then one this X minus. So it's nothing but ammonia NR4 positive X minus, NH4 positive X minus, ammonium chloride. So ammonium salt. So it's nothing but quaternary ammonium salt. Now it's treated with a base or a strong base OH minus, right? Because of this NR3 positive groups, the beta hydrogen is going to be slightly acidic, right? So I will have the reaction occurring via carbon ion pathway. So I will form carbon ion on that carbon which is relatively less substituted. Yes, because lesser is the substitution of carbon ion, higher is the stability of carbon ion. If the carbon ion is more substituted, the electron density will be more, stability will be less, right? So simply this base will attack on that beta hydrogen which is more acidic, or in an indirect way we can say it will attack on that beta carbon, or it will snatch hydrogen from that beta carbon which is less substituted. Students, you only tell me which beta carbon you find less substituted. Let's first of all talk about the beta carbon here. Can I say this one is going to be the beta carbon, this one as a beta carbon, alpha carbon, this one is once again the beta carbon, right? This one is once again the beta carbon. What do you say? Which beta carbon is least substituted here? This one, beta carbon. So what the base will do, it will snatch one hydrogen from here. As soon as it snatch, I will have the formation of carbon ion, will delocalize, and the entire leaving group will get departed, right? So this is the leaving group. I will have the formation of ethene, and this particular reaction is referred as Hofmann elimination. Why Hofmann elimination? Less substituted alkene is formed here, right student? Let's move ahead. Friends, that's all about today's classes. The topics which we have covered today: first, we have discussed basic strength, basicity. Then we move towards nucleophilicity and nucleophilic strength. We had done a lot of questions on these two topics. Then we move towards leaving groups. We had discussed the leaving ability of certain leaving groups. We were having good leaving groups, moderate leaving groups, poor leaving groups. And students, then at the end we had discussed different types of reaction, that is nucleophilic substitution reaction and elimination reactions, and we had discussed the different reactions pathway, their mechanism. So if I talk about the applications of these reactions mechanism, we'll do the applications in hydrocarbon, in the upcoming chapters alkyl halides, aryl halides, and even alcohol phenol ether. We are going to do a lot of application on these reactions and different reactions pathway. So that's it all. That's it.